9 days from disaster. A future Artemis habitat sits in near-permanent darkness, wedged into the jagged terrain near the moon's south pole. Outside, the landscape is silent, frozen at temperatures below -200 degrees Celsius in the shadowed craters. Inside, a soft red light flashes on a control panel, barely noticeable against the hum of pumps and fans. Pressure is falling, not by much, just fractions of a percent each minute, too slow to trigger the blaring alarms that mean instant death, too fast to ignore for long and still survive. The air in the small metal cylinder that keeps 4 humans alive is very gently, very quietly, trying to leave. The lunar atmosphere has a pressure equivalent of roughly 100 trillion times thinner than Earth's sea level pressure. A pinhole the width of a human hair could theoretically depressurize a 20 cubic meter habitat in under 6 hours, depending on the initial pressure gradient and seal material outgassing rates. Their suits hang on the wall, helmets locked, visors up. The crew is tired from a long EVA, boots still dusted with razor-sharp lunar regolith that grinds into seals and joints. For a while, no one looks at the tiny number on the screen that is starting to drift. Outside, there is nothing. No wind, no sound, no atmosphere to carry even the faintest vibration. The incredible part was always how empty the moon seemed from Earth. Up close, the thing is, that emptiness becomes a threat. It presses on every surface of the habitat, on every seam of every suit, waiting for the smallest weakness. Inside their helmets, when they go out, breathing will sound frantic and loud, but to the vacuum, it is completely irrelevant. There are only a few millimeters of metal and plastic between soft tissue and instant boiling of fluids. In other words, the difference between life and death is a human decision made through a scratched visor and a fogged HUD. The scary part is that at this distance from Earth, there are no quick rescues coming. No launch window in a few hours, no emergency return in a day. Artemis crews will live several days away from home, in places where a torn glove or a slow leak can play out long before anyone on Earth fully understands what is happening. The moon's south pole Shackleton crater has rim elevations of approximately 3,386 meters above the surrounding terrain, yet the crater floor remains in permanent shadow. This creates a thermal inversion where crater floors can be 5,100 degrees Celsius, colder than sun-facing slopes mere kilometers away. A microclimate so extreme that rover thermal management systems could fail in minutes if dragged into shadow. Here is where things get uncomfortable. This hypothetical slow leak, this half-noticed drop in pressure, is not an unthinkable surprise. It is a scenario already modeled in disturbing detail. Engineers have run simulations of micrometeoroids punching pinholes in habitat walls. Scientists have looked at what lunar dust does to filters, valves, and lungs over weeks. They have asked very specifically what would have happened if a warning light came on 9 days into a mission with no fast way home. They had no idea at first how many of those models would end with timelines that left almost no margin. The result was a quiet realization. Artemis is designed to push humans closer to that edge on purpose. Longer stays, harsher regions, more time in the shadows, all as a rehearsal for something even more dangerous on a world much farther away. So, the question hangs over every planned launch. How far is NASA willing to go, and how much risk is quietly being accepted in the name of exploration? NASA has already answered that question in a quiet, unsettling way. The next program is not designed to be safer than Apollo. It is designed to be more dangerous. Apollo was a series of raids, short, high-risk landings, tightly choreographed, in regions chosen because they were relatively flat and predictable. Crews touched down, spent a few days on the surface at most, collected samples, ran experiments, and then left. Every mission was built around a single, non-negotiable idea. There must always be a clear, fast path home. The landing sites reflected that mindset. No permanent shadows, no plunges into deep craters. No attempts to live with the moon, only to visit it. For a while, that was enough. The thing is, those missions never truly tested what happens when humans have to stay. Artemis is built around the opposite idea. Instead of brief encounters, it promises multi-week surface stays, repeated returns, and eventually a semi-permanent base. Instead of the equatorial plains, it targets the South Pole, a place with craters that sunlight never reaches. Inside those shadows, temperatures can fall below -200 degrees Celsius. In other words, this is not the safe moon that television audiences saw in the 1960s. The scary part is that this is intentional. NASA describes Artemis as a test bed for Mars, a proving ground where hardware, procedures, and human limits can fail in a controlled way before the stakes become months-long journeys in deep space. The moon is close enough to talk to, but far enough that help is never immediate. It becomes a laboratory for controlled failure. Lunar South Pole ice deposits are estimated to contain between 100 million to 1 billion metric tons of water ice, but much of it exists as dirty ice. Regolith mixed with ice at concentrations as low as 1 to 5% by mass. Extracting usable water requires heating and processing systems that would consume 30 to 40% of the extracted water as steam in sublimation. Here is where things get uncomfortable. Every Artemis crew is, in a very real sense, an experiment. Their bones, their immune systems, their eyesight, their sleep cycles, their mental health under weeks of isolation and constant danger, all of it will be monitored, measured, and pushed. Apollo astronauts saw brief flashes from cosmic rays passing through their eyes. Artemis crews will live in that radiation environment for far longer, with no thick atmosphere and no strong magnetic field above them. And the surface itself fights back. Lunar dust is razor sharp, electrostatically charged, and gets into everything. During Apollo, it clogged joints and irritated lungs in just a few days. On a mission that lasts weeks, the result was always theoretical. Under Artemis, scientists will find out what would have happened if those earlier crews had been forced to keep breathing and walking through it. The incredible part was that Apollo could still pretend to be temporary. Artemis cannot. Lunar regolith particles are typically 50–100 micrometers in diameter, but the sharp, jagged edges are the result of billions of years of micrometeorite impacts with no weathering. When tested in laboratory lung models, lunar dust analogs trigger inflammatory responses at concentrations as low as 1 microgram per cubic centimeter, roughly equivalent to breathing air inside a sandstorm on Earth, but with particles that never dull or round from friction. These missions will operate in darkness that lasts for days, in habitats that must not fail, with rescue always at least several days and one launch away. A torn suit near a shadowed crater, a micrometeoroid punching through a habitat wall, a medical emergency with no surgical team physically present. Each scenario becomes a test case for Mars. This video will go deeper into those scenarios, into the most disturbing realities and failure modes that come with turning the moon into a training ground, and what they quietly imply about the risks being prepared for beyond it. NASA's next landing zone on the moon is not a tranquil gray plain. It is a place where sunlight scrapes the horizon like a razor, and where, just a few steps away, the surface falls into a cold so deep that metal behaves like glass. This is the lunar South Pole. Unlike the equatorial sites visited by Apollo, this region is a maze of towering crater rims and knife-edged ridges. The sun never climbs high here. It just drags along the horizon, casting long, distorted shadows that stretch for kilometers. The result is a landscape that looks frozen in perpetual twilight. Just beyond those illuminated ridges are places where sunlight never arrives at all. Inside the permanently shadowed craters, temperatures plunge below -200 degrees Celsius. These are not just dark spots, they are true pits of night, where the interior has not seen direct sunlight for potentially billions of years. For scientists, that is exactly the point. Over eons, water molecules delivered by comets and asteroids are thought to have migrated across the lunar surface and become trapped in these cold traps as ice. Radar data and orbital measurements suggest that some of these shadows may hold vast deposits of frozen water mixed into the regolith. The incredible part was realizing what that actually means for exploration. Water is not just something to drink. Split into hydrogen and oxygen, it becomes air for habitats, an oxidizer, and fuel for rockets. A buried sheet of ice, locked in a crater wall, is effectively a buried cache of propellant and life support. The thing is, whoever controls those resources controls how far human missions can go, and how realistic it becomes to launch expeditions to Mars from the Moon instead of from Earth's deep gravity well. But here is where things get uncomfortable. The same conditions that preserve this ice also make these craters some of the deadliest places humans have ever attempted to work. The darkness is almost total. Helmet lights vanish into it after a few meters. Temperatures can destroy equipment in minutes if thermal control fails. Steep crater walls and loose regolith create slopes where a single misstep could send an astronaut sliding silently into a black pit, with no line of sight back to the habitat and no simple path out. The scary part is that Artemis is targeting this region precisely because it is so hostile. It is a deliberate stress test. Spacesuits, rovers, power systems, and even human psychology will be pushed against an environment that offers almost no margin for error. For a while, mission planners debated safer, sunnier sites. Eventually, the logic of using the hardest location as a proving ground for Mars won out. The result was a mission architecture built around chasing ice into the shadows. The permanently shadowed regions cover roughly 3,600 square kilometers, but only about 10% of that area is expected to contain economically extractable ice deposits. The remaining 90% is cold-trapped terrain. Pretty disturbing, given that the very resource needed most lies in places where rescue is least likely, where communications can be blocked by crater walls, and where even light itself barely reaches. What happens when something finally goes wrong in that darkness, and the only way out is deeper in? NASA's answer is not to back away from that darkness, but to walk directly into it. In other words, Artemis is designed as a controlled catastrophe that escalates on purpose. It starts gently, at least on paper. Artemis. I was an uncrewed test flight, a dress rehearsal where only hardware could die. Orion looped around the Moon, slammed back through Earth's atmosphere, and proved that the capsule, heat shield, and guidance could survive the basic profile. For a while, that looked reassuring. Nothing went obviously, publicly wrong. Artemis II changes one variable. This time, 4 astronauts ride the same path on a crude lunar flyby, skimming the edge of deep space without touching the surface. The trajectory is similar, but the stakes are not. Any flaw in life support, radiation shielding, or navigation now has human lungs and hearts attached to it. The scary part is that this is still considered the easy mission. It is just the baseline. Artemis III is where things get uncomfortable. Now the plan is to drop humans near the Moon's south pole, in terrain no one has ever walked. They will attempt multi-day surface stays, long EVAs across razor-sharp regolith, and operations near permanently shadowed craters cold enough to freeze metal. Suddenly, there are landers, suits, tools, power systems, and communication links that must all work together. Every added component is another way for something to fail in vacuum. After that, the missions stretch. Multi-day stays become multi-week expeditions. Scientists want more time on the ground, so NASA adds more equipment. Experimental habitats, larger power arrays, rovers, drilling rigs. Eventually, semi-permanent infrastructure has to survive the 2-week lunar night, when temperatures plunge below minus 170 degrees Celsius and solar panels go dead. Batteries, fuel cells, and radiators will cycle through brutal thermal swings again and again until one day they don't. This is not an accident. NASA talks openly about incremental risk. The thing is, there is no way to prepare for Mars without deliberately exposing crews to harsher and harsher conditions. Short missions become long ones, and the Moon becomes a laboratory for failure. The result was a philosophy where systems are pushed until they break, because scientists need to see how they break. That is the only way to know what would have happened on a 6-month trip to Mars, where help is months away. But every new capability multiplies the number of failure chains. Longer EVAs mean more time for a micrometeoroid to puncture a suit. More habitats mean more seals, more valves, more joints that can leak. More autonomy means more chances for a subtle software error to go unnoticed until it is too late. The incredible part was how routine this all sounds in technical briefings. On paper, it is just extended surface operations. In practice, it is more ways for a human being to be one thin layer of fabric away from vacuum. And behind the public charts, there is something else. Inside closed-door simulations, engineers model what happens when a lander tips, when a habitat wall is pierced at night, when a medical emergency unfolds in a crater where line-of-sight communication cuts in and out. They had no idea at first how quickly some of those scenarios cascade. Inside closed-door simulations, engineers model what happens when a lander tips, when a habitat wall is pierced at night, when a medical emergency unfolds in a crater where line-of-sight communication cuts in and out. They had no idea at first how quickly some of those scenarios cascade. A stuck hatch here, a misrouted power line there, and within minutes the timeline ends in irreversible loss of life. Pretty disturbing, considering those are the cases that rarely make it into press conferences. And the next phase of Artemis is built on pushing even closer to that edge. For Artemis crews, that edge will not just be a line on a risk chart. It will be the wall beside their bed. The surface habitat is, in the end, a pressurized metal and composite bubble sitting in a perfect vacuum. Inside, breathable air. Outside, nothing. No air, no pressure, no second chances. A few millimeters of aluminum alloys, carbon composites, and layered insulation will be all that stops that nothing from rushing in. The thing is, vacuum does not negotiate. When a human body is suddenly exposed, the air in the lungs tries to escape at once, tearing delicate tissue. The dissolved gases in blood and fluids begin to boil, not because they are hot, but because there is no pressure to hold them in. In other words, the body becomes its own leaking atmosphere. Within about 10 to 15 seconds, consciousness fades as oxygen in the blood is used up. Muscles convulse, saliva and tears start to bubble, and capillaries can rupture. The result was always the same in decompression accidents. Fatal damage in minutes. The scary part is that on the Moon, there is no outside air to rush back in. There is only vacuum waiting. Here is where things get uncomfortable. Every barrier between Artemis astronauts and that outcome has to work, every moment, for weeks at a time. Habitat walls must shrug off micrometeoroids arriving at several kilometers per second. Tiny fragments can hit with the energy of bullets. Windows and viewports have to survive, that while also enduring temperature swings of hundreds of degrees. Then, there is the dust. Lunar regolith is made of razor-edged glassy particles, electrostatically charged, clinging to suits, seals, and hinges. Apollo astronauts complained about it after just a few days. Artemis missions will stay for far longer. Suit joints, hatch gaskets, and airlock mechanisms will be grinding against that dust day after day. Scientists have watched seals stiffen, crack, and leak under far less hostile conditions. For the people inside, the physics becomes psychological. Imagine lying in a narrow bunk, aware that a single unnoticed crack, a slightly faulty valve, or a mislatched exterior door could turn the entire habitat into a silent tomb in seconds. No alarms loud enough, no rescue fast enough. Just a pressure drop curve on a console, and then nothing. The incredible part was always how quickly humans adapt to constant threat. Eventually, the sound of pumps and fans becomes background noise. The vibration of circulating air feels normal. But what if one of those sounds stopped at 3 a.m.? Just a pressure drop curve on a console, and then nothing. The incredible part was always how quickly humans adapt to constant threat. Eventually, the sound of pumps and fans becomes background noise. The vibration of circulating air feels normal. But what if one of those sounds stopped at 3 a.m.? Every night on the moon, crews will close their eyes knowing that the only thing between them and the void is a thin, aging shell built on Earth. And the next challenge will push them out into the darkness in suits that are themselves miniature, even more fragile habitats. Out there, the most dangerous failures will not begin with a bang. They will begin with a number that is off by just a fraction and stays that way for a little too long. On Artemis, that number is cabin pressure. Imagine a habitat sitting on the rim of a south polar crater. A fraction of a kilopascal over an hour. The software logs it, the sensors register it, but it looks like noise. Pressure shifts as equipment cycles, as temperature changes, as astronauts move. In other words, it looks normal. The scary part is that the system is only as good as its weakest sensor. Dust can coat pressure ports. Thermal swings can throw off calibration. A tired crew might glance at a trending graph and decide it can wait until after the next experiment run. For a while, nothing obvious happens. Here is where things get uncomfortable. Picture a lunar night in progress. 14 Earth days of darkness and brutal cold. Power is being carefully rationed. A small pressure dip appears on the console. It matches what the models say should happen when the air cools, or at least it seems to. The crew notes it in a log. One mentions that the life support loop has been noisy. Scientists on the ground can recommend options, but there is no resupply, no quick rescue, no spare habitat waiting over the horizon. What would have happened if the leak had started 3 days earlier, or if the remaining oxygen tank had a stuck valve? Scientists on the ground can recommend options, but there is no resupply, no quick rescue, no spare habitat waiting over the horizon. What would have happened if the leak had started 3 days earlier, or if the remaining oxygen tank had a stuck valve?
The incredible part was never the big explosions in space history. It is that so many missions survived long enough for those quiet numbers to drift back into the safe zone. On Artemis, some of the most disturbing failures may be nothing more than digits sliding the wrong way on a screen while everyone's attention is outside in the dark, and the next threat will be even harder to see coming. Those quiet numbers are one kind of invisible threat. The moon has another. It hangs in the air, clings to skin, and cuts like a cloud of microscopic knives. Lunar regolith dust looks harmless in photographs. In reality, it is made of shattered rock and glass fragments, broken apart by billions of years of impacts, not by wind or water. There is no weather on the moon to round the edges, no erosion to smooth anything down. The result was a powder where every grain is a jagged blade. Under a microscope, those grains resemble tiny shards of broken window, fused with metallic splinters and volcanic glass. In other words, every step an astronaut takes grinds more of this material into even finer, sharper particles. Those particles can slice into lungs, eyes, and the flexible layers of a spacesuit just as effectively as sandpaper chews through paint. Lunar regolith contains a significant fraction of particles smaller than 10 micrometers, the respirable fraction that can penetrate deep into lung tissue. Additionally, the regolith is rich in iron oxides and ilmenite, iron titanium oxide, which when finely divided can generate free radicals in biological systems. The scary part is that the dust does not just sit on the ground. Bathed in harsh solar radiation and bombarded by charged particles, it becomes electrostatically charged. It floats, it leaps, it clings. Suits, tools, visors, cables, even the seals around airlocks become magnets for this gray, toxic snow. Apollo crews discovered this the hard way. They had no idea what walking on the moon would do to their equipment and bodies over just a few days. After each moonwalk, they tracked dust into the lunar module despite careful brushing. It coated controls, jammed mechanisms, and worked its way into joints and hinges. Astronauts described a burning gunpowder-like smell and reported hay fever-like symptoms, coughing and irritated eyes, after breathing trace amounts that slipped inside. For a while, those symptoms faded once they left the surface. On Artemis, that assumption becomes dangerous. These missions are not 3 days in a fragile lander. They are planned as weeks or even months around the lunar South Pole, with repeated excursions, repeated suit cycles, and repeated chances for dust to infiltrate habitats. Here is where things get uncomfortable. Repeated inhalation of razor-edge mineral dust is not just an annoyance. On Earth, long-term exposure to fine silica and similar particles leads to lung scarring, chronic inflammation, and cancer. Lunar dust is at least as sharp and possibly more reactive thanks to unweathered surfaces and embedded metals activated by radiation. Imagine a habitat where every filter, every gasket, every fabric surface is slowly colonized by this material. Even tiny leaks in suit bearings or airlock seals could allow invisible grains to circulate for years. The entire surface environment becomes a slow, ever-present health hazard, turning each breath into a calculated risk. And the thing is, engineering solutions are still experimental. Electrostatic dust repellent coatings, advanced filtration, dedicated suit ports that keep suits outside the habitat. All of these are promising, but none has been proven over Artemis-level timescales. What would have happened to an Apollo crew if they had stayed another month in that environment? No one truly knows. The incredible part was that Apollo could always leave in an emergency and be home in days. Artemis keeps that safety net barely. Mars will not. If lunar dust cannot be fully controlled on a world only a few 100,000 kilometers away, what does that imply for a mission where medical evacuation is impossible and the local dust may be even more chemically active? The next environment may not just cut, it may react. Some of the most disturbing problems, then, are not the obvious explosions or dramatic failures. They are the quiet abrasions, the slow poisoning, the unseen damage building up in lungs and machinery at the same time. And the next threat on Artemis will not come from the ground at all, but from something that moves too fast to see and never stops falling. Radiation on the moon does not roar, it whispers. On Earth, storms announce themselves with clouds, thunder, warnings that scroll across screens. Around an Artemis base, the most dangerous storm will arrive in silence, made of particles moving close to the speed of light, passing straight through skin, metal, and bone. The thing is, Earth cheats. A global magnetic field and a thick atmosphere catch most of the high-energy debris pouring out of space. The result is a protective cocoon that life has quietly depended on for billions of years. The moon has neither. No global magnetic shield, almost no atmosphere. In other words, Artemis crews will live on a bare rock, with only their spacecraft and habitat standing between their cells and the universe. Out there, two main threats never go away. One is the constant drizzle of galactic cosmic rays, particles accelerated by distant supernovas and black holes. The other is the more local, more violent outbursts from the sun. Both can shatter DNA like glass. Both are invisible. Here's where things get uncomfortable. Radiation dose is hard to feel, but easy to compare. A single full-body CT scan delivers a noticeable hit to human tissue. Now imagine stacking several of those scans, not in a hospital, but spread over weeks in partial gravity and dust. Months on the lunar surface can quietly add up to the equivalent of multiple CT scans. Full body, layered one on top of another. The damage is cumulative. Strands of DNA break, repair systems misfire, mutations slip through. The scary part is that the consequences may not appear for years, long after the mission is celebrated as a success. Then there are the real storms. Sometimes the sun hurls out vast eruptions of plasma and magnetic field. It is a massive cloud of charged particles shot out from its surface at incredible speed. Scientists call this a coronal mass ejection. When one is aimed at the moon, radiation levels can spike in minutes. For an Artemis crew outside on an EVA, that matters. A badly timed spacewalk during an unexpected solar particle event could deliver a life-altering dose in just a few hours. Skin, eyes, bone marrow, even the heart all take the hit. The result was modeled for decades on paper and in computers, but on the surface, the countdown would be real. Get back, get inside, get behind shielding. The incredible part was how primitive the warning system still is. Space weather forecasting has improved, but predicting the exact timing, intensity, and direction of these events is still imperfect. There are alerts, there are models, but there's also uncertainty. For a while, astronauts might not know whether a flare on the sun is a harmless flash or the front edge of a lethal wave. Inside the habitat, storm shelters will be the last line of defense. These are cramped, heavily shielded sections, often surrounded by water tanks, food, and equipment to soak up radiation. During a major event, crews may have to crowd into these spaces for hours, possibly longer, with limited room, limited comfort, and a constant awareness that metal and plastic are all that stand between them and a dose that could end a career or a life decades early. And this is the quiet gamble built into every Artemis mission. Schedules can be planned, budgets controlled, trajectories calculated, but cosmic rays and solar storms do not care about launch windows or human ambition. They arrive when they want, in patterns that still defy full prediction. The disturbing question hanging over each long-duration stay is simple. What would have happened if the next great solar storm, the next unseen blast, chose that exact week to hit? Eventually, Artemis planners will have to confront an even harsher version of that question on a voyage where there is no sheltering moon and no quick return at all. That harsh version starts in a place that looks deceptively calm, a silent gray plain turning from blinding white to pitch black over the course of a month. On the moon, a day does not last 24 hours. It lasts about 29.5 Earth days. In other words, roughly 14 days of relentless sunlight, followed by 14 days of unbroken night. During the long lunar noon, sunlit ground can climb to around plus 120 degrees Celsius. In the darkness, that same surface can plunge below minus 170. For Apollo, this was a background hazard. Short stays, carefully timed landings, and quick departures meant the worst swings were often avoided. Artemis is different. Artemis is designed to sit in that environment, to ride through those transitions again and again. Metal frames, joints, and tanks will expand for days, then contract for days, over and over, in a slow mechanical heartbeat that never stops. The scary part is what that does over time. Every seal, every weld, every window frame will be breathing with the heat. Microscopic cracks can open and close. Rubber and composites can gradually lose flexibility. The result is material fatigue, the quiet cumulative damage that does not announce itself until something finally fails. Engineers can model this on Earth, but lunar reality will be harsher than any test chamber. Here is where things get uncomfortable. Artemis is not just targeting any part of the moon, it is aiming for the south polar regions, where permanently shadowed craters never see direct sunlight at all. Inside those craters, temperatures can drop below minus 200 degrees Celsius. That is colder than almost anywhere on Earth's surface, closer to the temperatures of the outer planets than to a desert night. Any equipment that operates there will be pushed to the edge of known engineering limits. Lubricants can freeze. Electronics can behave unpredictably. Metals that are tough at room temperature can become brittle. For a while, some of these systems might appear to work normally. Then a hinge snaps, a connector fractures, or a cable sheath shatters with almost no warning. Outside the craters, the problem flips. Habitats sitting in sunlight must reject enormous heat by day, then somehow stay warm through a 2-week night when solar power is limited or gone. That means batteries, fuel cells, or compact nuclear sources running continuously with almost no margin for error. What would have happened if one of those power lines shorts in the 12th night, when everything outside is colder than dry ice? Inside the habitat, the incredible part was how narrow the safe band really is. A shift of just a few degrees too cold, and water in lines can freeze, valves can seize, filters can crack. Outside, metal turns brittle and plastic stiffens. Inside, a stuck pump or frozen sensor can cascade into life support that simply stops working in the dark, leaving a small human outpost surrounded by a world of fire and ice. Eventually, planners have to ask a disturbing question. How many nights like that can a system survive before the odds finally turn? Eventually, planners have to ask another question. What happens when that fragile life support has to walk away from the habitat and balance on the edge of a cliff made of vacuum? This is the Artemis South Pole, EVA. 2 astronauts in white suits, moving along the razor-thin rim of a crater that has never seen sunlight. Below them, the interior falls away into permanent shadow, colder than anything on Earth. Above them, the sun hangs low, casting long, confusing shadows across jagged rock. The lander is not always visible. Terrain blocks the view, hills and boulders swallowing the bright shape that brought them here. In the distance, there might be only a faint glow on the horizon where floodlights from the habitat bounce off dust. In other words, the nearest safe air is out of sight, and sometimes only barely in reach. They move in low gravity, feet touching down in slow, exaggerated steps that look graceful on camera and feel anything but. Each astronaut is tethered to a rover or to fixed anchor points, because one misjudged push can send a body drifting in a slow, unstoppable arc toward that black interior. The scary part is that in 1/6 gravity, momentum is gentle but merciless. It does not care that the drop is silent and airless. Inside each suit is an entire life support system shrunk to backpack size. oxygen tanks, scrubbers, pumps, fans, valves, batteries, cooling loops. It looks robust. It is not. Any failure in that chain starts a clock that runs fast. A stuck valve can mean rising pressure. A failed pump can mean cooling stops and the astronaut begins to overheat. The result was measured on past missions in minutes, not hours, and Artemis pushes those margins even harder. Here is where things get uncomfortable. At the lunar South Pole, the sun barely clears the horizon, so light skims sideways across the ground. Shadows stretch for tens of meters, and deep pockets of darkness swallow detail. Depth perception breaks down. What looks like a gentle slope can be a sudden drop. What seems like solid ground can be a fractured ledge hanging over emptiness. For a while, an astronaut might not even realize the risk. Helmet glare, drifting dust, and the constant need to monitor suit readouts compete with the simple task of walking. Scientists know that human balance systems evolved for a world with air, sound, and clear visual cues. The moon has none of that. Communication becomes the last safety net. Suit radios tie each astronaut to the partner, to the rover, to the distant, unseen habitat, and to controllers back on Earth with their checklists and contingency plans. Lose that link, and a person can be standing 10 meters away and still be effectively alone on the moon. They can wave, gesture, even scream, and nothing passes through the vacuum. The lunar South Pole terrain creates communication dead zones that are not uniform. Depending on landing site selection within the Shackleton crater region, crews could experience intermittent line of sight to relay satellites for periods of 2 to 8 hours per lunar day, with blackout windows unpredictable due to dust storms and electrostatic phenomena that degrade radio signal strength even when line of sight theoretically exists. The signal degradation caused by lunar dust ionization during sunrise/sunset terminator passages is still not fully characterized. The incredible part was how often Apollo relied on that invisible thread without incident. Artemis will stretch it farther into terrain no human has crossed. So what happens if an astronaut, distracted by an alarm or blinded by glare, places one boot wrong on that rim? Imagine a slip, not a dramatic fall, just a slow slide of regolith under a metal foot, a center of mass shifting a few centimeters too far. The tether snaps taut, or maybe it doesn't. The astronaut tips, weightless for a fraction of a second, then begins to tumble over the edge, still breathing, still conscious, suit intact, but moving down into radio-shadowed darkness. They had no idea in that instant whether the line would hold, whether the rover could pull that mass back up, whether there was even enough oxygen left for a rescue attempt. The thing is, on the moon, out of reach and out of time can arrive at exactly the same moment. And if that happens during an Artemis EVA, with the habitat just a faint glow beyond the horizon and the clock already running down inside the suit, the next question is even more disturbing. Who decides when to stop trying to pull them back? In some Artemis scenarios, the ending is not an explosion or a dramatic crash. It is a voice getting quieter, and then nothing. Imagine the chain starting with something almost trivial, a fine mist of lunar dust kicked up by a rover wheel, drifting in the weak gravity, clinging electrostatically to a helmet. The visor goes from crystal clear to a smeared gray filter. Visibility drops. The astronaut takes a careful step on a slope that looked flat a moment ago and misjudges the angle. One boot slips on loose regolith. The body twists, momentum carrying just far enough to slide behind a low ridge. Line of sight to the rover and to the other astronaut is gone. The suit radios crackle, a brief glitch as the antenna dips below the horizon of local terrain. For a while, there is only breathing and static. The scary part is that on the moon, that is all it takes. No stars visible against the bright surface, no trees, no buildings, almost no landmarks at all, just repeating ridges and shadows. In other words, every direction looks the same, and the clock inside the suit is still counting down oxygen and battery. Turning quickly is hard. Running is almost impossible. These are not sleek science fiction suits. They are pressurized balloons of fabric and metal, fighting every motion. Low gravity helps with weight, but not with inertia. Each step is a controlled hop that risks another fall, and each fall can damage joints, hoses, or the life support backpack. The result is that even a few hundred meters become a serious problem. At lunar South Pole distances, that can be the difference between being able to see a habitat beacon and being trapped in a blind pocket of terrain. Scientists designing Artemis know this, which is why early missions will lean heavily on line-of-sight visuals and local radio beacons instead of a full GPS-style satellite network. Here's where things get uncomfortable. Those beacons can fail. Antennas can be shadowed by crater rims. A rover can slip behind a boulder field. Without a dedicated navigation constellation around the moon, there is no simple turn left 50 meters rescue instruction. Mission control can only see telemetry, not the detailed shape of every ridge around the stranded astronaut. And the other crew members, they may be working near permanently shadowed ice deposits, already at the edge of their own consumables, tethered by power umbilicals or safety lines to critical equipment. To reach the lost astronaut, they might have to disconnect from those lifelines, drive a rover into unknown terrain, or push their suits into red zone margins that were never meant to be crossed. What would have happened if one attempt fails and now two suits are low on oxygen? The incredible part was how often Apollo crews depended on nothing more than memory and horizon features to find their way back. Artemis will push farther into more broken landscapes where that is no longer enough. In some scenarios, the math becomes brutal. One astronaut can be saved, or all of them can be lost. There is no third option. Mission Control runs simulations in real time, watches numbers slide towards zero, and knows that any order to go after them might only create more bodies. Eventually, the pattern of data on the screen begins to thin. Heart rate, suit pressure, oxygen partial pressure. Then one by one, the lines flatten. Controllers on Earth are still talking, offering bearings, calm instructions, and finally just words meant for a person who can no longer respond. The scary part is that this is not a theoretical horror invented for drama. It is a known risk, quietly written into procedures and contingency plans. And as Artemis missions grow longer and more ambitious, the next disturbing question becomes unavoidable. What if the first permanent human presence on the moon also means the first permanent human remains? On the moon, the boundary between alive and gone can be as thin as a few millimeters of fabric. A spacesuit looks like clothing. In reality, it is a small, fragile spacecraft wrapped around a human body. Under the white outer shell, there are multiple layers of woven fabric, insulation, metal rings at the joints, and finally a pressure bladder that actually holds in the air. It runs at a fraction of Earth's sea level pressure, just enough to keep blood and tissues stable. The thing is, that thin artificial atmosphere is all that stands between an Artemis astronaut and instant vacuum. Lunar regolith is not soft dust. It is razor-edged, glassy powder that has never been rounded by wind or water. A sharp rock on a crater rim, or a micrometeoroid moving faster than a rifle bullet does not care how advanced the mission patch looks. Here is where things get uncomfortable. There are really two main kinds of suit failure. One is explosive decompression, a large tear, a ripped seam, a shattered visor. In that scenario, pressure can collapse in seconds. Air rushes out, moisture in the lungs boils, and within about 10 to 15 seconds, consciousness fades. In other words, by the time a hand reaches for a valve, the brain is already shutting down. The other scenario is quieter, but just as disturbing. A tiny puncture, a slow leak. Pressure starts to drift down instead of crashing. At first, the astronaut might only notice a warning tone or a subtle stiffness in the gloves. Depending on the size of the hole, there might be minutes. In a best-case small leak situation, maybe 30 minutes, maybe 3 hours before the suit crosses the line where blood oxygen can no longer keep the brain functioning. Scientists model this with simple numbers. If a suit is holding at roughly 1/3 of Earth's pressure and a leak is venting a few liters of air per minute, software can predict when critical thresholds will be reached. Loss of useful consciousness might come after only a few minutes of degraded pressure, even if the heart keeps beating for much longer. What would have happened if this started at the far edge of a traverse, 2 kilometers from the habitat, in rough terrain and low gravity? Emergency patches exist. Self-adhesive pads, clamp-on cuffs, redundant layers designed to close around small punctures. The incredible part was how often test crews in analog environments forgot to use them immediately or misjudged the severity of a simulated leak. Awareness and time are essential, and during a complex EVA on a sloping crater wall, both can disappear frighteningly fast. The scary part is that on Artemis, there will be no rescue helicopters, no trauma team rushing out from behind a blast door. There will only be the crew, the tools they are already carrying, and a suit that is either holding pressure or silently failing. Eventually, another disturbing question emerges. If a suit breach is survived, what other systems on the moon are waiting to fail next? On Artemis, surviving the vacuum outside is only half the problem. The more disturbing threat is that the habitat designed to keep astronauts alive can, under the wrong conditions, quietly turn against them. Inside that pressurized shell, an entire ecosystem runs nonstop. Oxygen has to be generated, stored, and metered into the air. Carbon dioxide has to be stripped out and trapped. Temperature and humidity are held in a narrow band where human lungs and electronics can function. Water is filtered, distilled, and recycled. Waste is collected, processed, and sealed away. In other words, life support is not one machine. It is a chain of machines, all of them critical. The scary part is that most failures will not look dramatic at first. Filters clog a little faster than the software predicted. A valve in the oxygen line sticks halfway, not fully open, not fully closed. A condensation sensor in the cooling loop starts reporting numbers that are slightly off. For a while, everything still feels normal. The habitat hums, the lights are on, the fans are running. Here is where things get uncomfortable. In a closed environment, small deviations add up. A carbon dioxide scrubber cartridge saturates early and is not replaced in time. The result is a slow, invisible rise in CO2 levels. At first, it just feels like mild fatigue after a long EVA. Then the headaches start. Breathing feels oddly unsatisfying. Concentration slips. Scientists have seen this before on space stations in low Earth orbit. On the moon, the margin is thinner. As CO2 climbs, judgment degrades. Crew members become irritable, make simple mistakes, misread procedures. The incredible part was how insidious this became on earlier missions. The very people who needed to troubleshoot the system were being quietly impaired by it. Now imagine that playing out in an Artemis habitat near the lunar South Pole. Outside, temperatures in nearby shadowed craters fall below minus 200 degrees Celsius. Going out to swap hardware under those conditions is already dangerous. Inside, the crew stares at a screen of warning codes, trying to remember which line of the checklist comes next, while the gas in their lungs keeps getting heavier. They had no idea at first which component was failing. Was it a stuck valve in the CO2 removal bed, a software glitch misreading partial pressure, or a tiny leak in a duct behind a wall panel? On Earth, technicians would roll over a cart of spare parts. On Artemis, only a limited stock of filters, valves, circuit boards, and tools exists, carefully chosen for mass and volume. What happens when the wrong part fails? Some problems will demand improvisation with tape, spare tubing, packaging foam, even pieces of equipment never meant to be life support hardware. It worked on Apollo 13. On a long-duration lunar base, that kind of ad hoc repair might have to last for months. The thing is, every improvised fix adds uncertainty. Did that patch introduce a new leak path? Will the modified water loop grow biofilm that clogs it weeks later? The habitat keeps humming, but trust in its systems erodes. Eventually, a disturbing realization settles in. Millions of kilometers of empty space are not the only threat. In a sealed habitat on the moon, the line between safe refuge and lethal trap is exactly as thin and exactly as fragile as the machines built to maintain it. In a sealed lunar habitat, the most dangerous thing might not be the vacuum outside, it might be a spark. On January 27, 1967, 3 Apollo astronauts climbed into a ground test capsule in Florida. The cabin was pressurized with pure oxygen, slightly above atmospheric pressure. Technicians outside heard a shout, a cry about fire, and then the audio cut into chaos. In less than a minute, flames turned the interior into an oven. The scary part is how fast it happened. The wiring, the Velcro, the suits, even the checklists on paper, everything that could burn did. In a high oxygen environment, materials do not just catch fire, they erupt. The result was a blackened shell that investigators had to cut open from the outside because the hatch jammed under pressure and heat. 3 decades later, in 1997, a different fire broke out on the Mir space station. This time, it was a solid fuel oxygen generator, a small device meant to keep the crew alive. It malfunctioned and produced a jet of flame that shot across the module like a blowtorch. The corridor filled with thick smoke. Cosmonauts groped for masks, some finding them by touch alone. For a while, no one was sure if the fire would reach stored oxygen tanks or fuel lines. Here is where things get uncomfortable. There was nowhere to run, and opening a hatch to space was not an option. The crew managed to smother the fire, but the station stayed filled with toxic smoke for hours. The incredible part was that it did not end with an evacuation or a funeral. Artemis missions will inherit all of that history. Their habitats and spacecraft will still rely on concentrated oxygen, polymer walls, wiring looms, foam, fabrics, and stored chemicals. In other words, they will be careful stacks of flammable material wrapped in pressure shells. Engineers can remove ignition sources, add sensors, and demand clean procedures. But an electrical short, a damaged cable behind a panel, or an unexpected chemical reaction can never be reduced to absolute zero. On the moon, fighting the resulting fire becomes its own nightmare. There is no outside atmosphere to vent smoke into, only vacuum that will also strip away pressure and heat control. Extinguishers are limited, both in number and in type. Spraying water or foam risks shorting critical electronics. Letting the blaze burn is unthinkable. Yet depressurizing a module to snuff the flames could cause decompression sickness, embolisms, or outright asphyxiation before the fire ever dies. Imagine an Artemis night at the lunar South Pole. Outside, the crater rims glow faintly in reflected Earthlight, while the interior of the habitat hums with recycled air and quiet fans. Then a sharp chemical smell, an alarm. Red lights pulse as sensors detect a temperature spike behind a wall rack. A panel suddenly blisters and splits, and flame punches into the cabin, longer and wider than a normal Earth fire because of the enriched oxygen. In seconds, visibility drops as smoke and vaporized plastics fill the air. Crew members scramble for portable masks, fighting against bulky suits and narrow passageways. One tries to reach the main power distribution box, knowing that cutting power might stop the short, but might also shut down pumps and life support loops. Another drags an extinguisher toward the source, while a third is already watching readouts climb on a nearby oxygen tank. The thing is, every decision now is a trade. Spray too much suppressant and risk contaminating filters, or hold back and let the fire eat through a cable bundle that keeps the habitat warm. What would have happened if the flame breaches a pressure seal? If it weakens a structural ring that holds a docking port in place? In a sealed environment, a fire is not just a local emergency. It is a threat to every lung drawing breath inside, to the integrity of the shell itself, and to the mission's survival. And if that shell fails, the next problem Artemis crews face may be even more disturbing than fire. On the moon, a twisted ankle is not a minor inconvenience. It can be the first link in a chain that ends with a body sealed in a flag-draped bag, waiting for a ride home that may never come. Artemis crews will live and work days away from Earth in places where the nearest hospital is a blue-white dot in the sky. In that environment, almost any medical emergency becomes disturbing. A stumble on uneven regolith can turn into blunt force trauma inside a spacesuit. A misstep on a ladder can mean broken ribs, internal bleeding, or a fractured spine. Add in radiation sickness from a solar storm, heart attacks in middle-aged, highly stressed bodies, appendicitis, deep infections, and psychological breakdowns under relentless isolation. And the moon starts to look less like a destination and more like a trap. The scary part is that the tools available there will look nothing like an emergency room on Earth. Artemis missions will carry limited medical kits, some diagnostic equipment, and at least one crew member with advanced medical training. There will be defibrillators, basic drugs, splints, and bandages, but no full surgical suite, no blood bank, no intensive care unit humming quietly in the next room. In other words, no way to perform the complex, hours-long interventions that routinely save lives on Earth. Instead, the backup hospital is Earth itself, reached only through a time-delayed video link. Telemedicine will be the main lifeline, with surgeons and specialists watching grainy feeds from thousands of kilometers away, trying to guide hands that are shaking inside a pressurized habitat. Even if the moon to Earth delay is only a couple of seconds, it breaks the illusion of real-time control. Remote robotic surgery sounds incredible in presentations, but here is where things get uncomfortable. A dropped instrument or a sudden change in vital signs cannot be fixed by someone who is not physically there. For a while, mission planners focused on dramatic crises. compound fractures, chest trauma, decompression. But the thing is, it may be the routine conditions that prove most lethal. A kidney stone on Earth is agonizing but manageable. On the moon, the pain can cause vomiting inside a helmet, dehydration in a closed loop life support system, and immobilization when every EVA is on a strict timeline. A severe allergic reaction that would earn a quick ambulance ride on Earth could, in a lunar habitat with limited epinephrine and no ventilator, become a slow suffocation. Psychological collapse is just as scary. Weeks in confined modules, under harsh schedules and constant danger, can trigger panic attacks, depression, or psychosis. They had no idea during Apollo how close some crews might have been to breaking under far shorter missions. Artemis will push far beyond that. The incredible part was never that Artemis would be safe. It was that planners must quietly decide in advance what level of suffering and risk is acceptable. The result was a set of medical protocols that effectively admit something pretty disturbing. Some conditions will simply be untreatable on the moon. Evacuation windows are limited by orbital mechanics, weather at landing sites, and the health of the rest of the crew. There will be scenarios where the only option is palliative care in 1/6 gravity. So what does it mean to volunteer for a mission where a kidney stone, a burst appendix, or a sudden psychotic break could become a death sentence? Not because medicine does not exist, but because of where the patient happens to be in the solar system. In other words, there are going to be moments on Artemis when the most advanced mission control center on Earth is effectively just a spectator. The moon feels close. It is only about 384,000 kilometers away, and radio waves cross that distance in a little over a second. But the result was something that sounds trivial on paper and becomes disturbing in practice. Roughly 1.25 seconds each way, about 2.5 seconds round trip. That delay does not sound like much. It is less time than a heartbeat. The scary part is that human conversation, especially under stress, depends on instant feedback. On the moon, every question, every answer, every shouted warning arrives slightly out of phase with reality. Voices overlap. People talk over each other. Instructions arrive just after the moment they were meant for. During Apollo, this was already obvious. Astronauts occasionally stepped on mission control's words, or paused awkwardly, waiting for a response that had not even left Earth yet. For routine checklists, that was just mildly annoying. For a fire in a habitat, a torn suit, or a sudden loss of pressure, those same 2.5 seconds become an eternity. Imagine an Artemis crew member reporting a hiss, a pressure drop, a burning smell. By the time the call reaches Earth, the situation has already changed. Controllers answer based on an earlier snapshot of reality. Here is where things get uncomfortable. Any advice they give is, by definition, late. Remote control is no escape hatch either. On the International Space Station, ground teams can sometimes take direct control of systems. On the moon, that lag turns precise teleoperation into guesswork. A robotic arm moved from Earth will always be chasing where a target was, not where it is now. In a fast-moving emergency, that is pretty disturbing. So Artemis is being built around a different idea. Crew autonomy. Astronauts will be trained to diagnose, decide, and act without waiting for permission, because waiting could mean hypoxia instead of survival. The thing is, this is not a philosophical choice. It is physics. Rapid decompression from a micrometeoroid hit can kill in seconds. A suit puncture on the surface leaves almost no time before loss of consciousness. A flash fire in a cramped module can go from first whiff to unbreathable in less than a minute. In these scenarios, by the time mission control even understands what happened, the event will already be over one way or another. The incredible part was how long the illusion lasted, that the moon was just an extension of low Earth orbit, only a bit farther away. Artemis quietly breaks that illusion. In this environment, Earth can advise, analyze, and reconstruct what would have happened if different choices were made, but it cannot reach through the delay and pull anyone out. The moon becomes something else instead, a place close enough to talk to, but too far to save. And that raises a darker question for the next phase of exploration. If this is the reality only 2.5 seconds away, what does it look like when the delay is minutes long, not seconds? On the lunar South Pole, that delay stretches into something else. Not just time, but darkness. Artemis is deliberately aiming for regions where the sun barely skims the horizon and where some craters never see it at all. Inside a habitat parked near that eternal shadow, the outside world is mostly an abstraction. No blue sky, no sunrise, just metal walls, recycled air with a faint chemical smell, and overhead panels set to whatever color temperature mission planners decide. The thing is, the human brain did not evolve for this. It expects light and dark to mean something. On the moon, the natural day is almost 28 Earth days long. 2 weeks of light, 2 weeks of night. Artemis crews will not be able to follow that. Instead, they will live on an artificial schedule, walking through a manufactured morning under LEDs, then trying to convince their bodies it is night, even when instruments outside still register harsh, unfiltered sunlight or total black. Circadian rhythms can be pushed, but only so far. On the International Space Station, astronauts already report insomnia, fragmented sleep, and mood swings. Now stretch those stressors across multi-week surface stays, add a light cycle that makes no intuitive sense, and remove any real window that shows a familiar sky. The result was predictable in simulations: slower reaction times, impaired memory, and a creeping emotional flattening that can turn dangerous in an emergency. Here is where things get uncomfortable. In a place where a torn glove or a failed pump can kill in minutes, every sound becomes a potential threat. A faint rattle in the wall might be a harmless fan bearing, or it might be a slow leak. A brief alarm could be a sensor glitch, or the first and only warning of a pressure drop. Living for weeks in that environment creates something close to chronic hypervigilance. Hearts spike at every unexpected vibration. Sleep is lighter, shorter, and less restorative. The scary part is that this constant scanning for danger is necessary for survival, but it quietly erodes the very mental resilience needed to respond when something actually goes wrong. Then there is the social pressure cooker. Artemis crews will be small, sealed into a volume not much larger than a small apartment, with no way to step outside alone unless fully suited and cleared. Every personality quirk is amplified. Minor annoyances, someone's eating habits, a way of speaking, a different approach to risk, can, over time, feel almost unbearable. On Earth, people can walk away from conflict. On the moon, there is literally nowhere else to go. Family is a distant voice delayed by seconds, filtered through scheduled calls and bandwidth limits. For a while, that novelty might feel incredible. Eventually, it becomes a reminder of everything that cannot be reached. Psychologists have tried to model what would have happened during extended polar missions in Antarctica, in submarines, and in isolation chambers. Those analogs show rising tension, withdrawal, and occasionally breakdowns. But they had no idea how much the knowledge of a vacuum outside and a black crater that has not seen sunlight for billions of years will add to that load. In other words, the most disturbing unknown about Artemis is not whether bodies can survive the radiation, the dust, and the cold. It is whether minds can remain stable in a place where the night beyond the hatch never truly ends, and where the next step after the moon is an even longer darkness with no quick way back at all. For decades, scientists have tried to rehearse this darkness on Earth. The result was a series of controlled experiments that look impressive on paper and strangely fragile when compared to what Artemis is actually designed to do. On the slopes of Mauna Loa in Hawaii, crews have lived for months inside a dome as part of HISEAS. Outside was barren rock and thin air. Inside was a closed habitat where every exit was supposed to feel like stepping onto another world. In Russia, at facilities like NEK in Moscow, volunteers have been sealed into metal modules, mimicking the cramped corridors of a deep space vehicle. In Antarctica, winter-over teams at places like Concordia Station endure months of isolation, no sunlight, and temperatures that would kill unprotected humans in minutes. These are called analog missions. In other words, Earthbound stand-ins for the confinement and isolation of spaceflight. For a while, they have been the main way to probe what happens to minds when escape is not an option. They generate valuable data. Group dynamics under stress, how small conflicts spiral, which coping strategies work, and which quietly fail after the 100th day. The incredible part was how predictive some of these patterns became for real missions in orbit. But here is where things get uncomfortable. None of these analogs contain a real vacuum on the other side of a few millimeters of metal. No one lies awake at night knowing that a single torn suit or a micrometeoroid through the wall means death in seconds, not an incident report and a debrief. HISEAS crews could always open an emergency hatch. NEK participants could walk out of the module. Antarctic teams, as isolated as they feel, still exist under a sky with breathable air and the possibility of evacuation, even if delayed. The scary part is that Artemis is being built for places where those safety valves simply do not exist. Lunar South Pole habitats will sit in a landscape of razor-sharp dust, deep shadow, and radiation that slips easily through human tissue. Communication delays will be short but constant. Medical emergencies will unfold days away from a real operating room. What would have happened in an analog becomes, on the moon, what is happening right now. Ethics draw a hard line on Earth. No review board will approve an experiment that exposes subjects to non-trivial chances of dying in a vacuum or suffocating in a collapsed habitat. The result is a permanent gap between what can be simulated and what Artemis crews will actually face. So Artemis itself becomes the experiment. Every long-duration surface stay, every multi-week mission into regions that have not seen sunlight for billions of years will double as a live test of human psychology under unprecedented conditions. And the disturbing part is that the data will be written in real lives, not questionnaires. Some failure modes can be modeled: irritability, sleep disruption, slow building depression. Others cannot: panic in the middle of a depressurization event, a breakdown during an EVA in permanent shadow, a dangerous decision made after one risk too many. They had no idea, past crews will say, how thin the line actually was. Artemis was never just about going back. It was about finding out how close human beings can get to the edge and still function. NASA has been unusually clear about this. In briefings and strategy documents, Artemis is described as a test bed for Mars. In other words, the moon becomes a controlled environment where systems, procedures, and human performance will be stressed on purpose so that failures happen now, in the relative safety of a 3-day return, instead of months away across interplanetary space. The scary part is what that actually means in practice. Multi-week missions near the lunar South Pole will send small crews into regions no Apollo astronaut ever saw. Permanently shadowed craters colder than minus 200 degrees Celsius, razor-sharp regolith that grinds into lungs and seals, radiation exposure that never really turns off. Every habitat leak, every suit abrasion, every life support glitch becomes data. The result was always meant to be a playbook for Mars. Here is where things get uncomfortable. Those data points are people. Astronauts are not naive. They are highly trained volunteers who sign up knowing that a micrometeoroid, a bad valve, or a moment's distraction can end everything in seconds. But informed consent depends on understanding the risks. How does anyone truly comprehend the full spectrum of unknowns involved in living for weeks in a place where no human nervous system has ever been tested that long, under that kind of isolation and constant threat? For a while, even mission planners will only be guessing. Long-duration lunar dust inhalation, subtle radiation damage to the brain, psychological strain from operating in endless darkness, with Earth hanging above the horizon but always out of reach. They had no idea, Apollo crews will say in hindsight, what would have happened if those missions had lasted 3 times longer. There is also a disturbing asymmetry built into the whole architecture. A handful of people accept extreme, possibly irreversible danger, so that millions who will never leave Earth can gain knowledge, technology, and eventually maybe even a path off the planet. The thing is, society benefits either way. The individual either survives and becomes a data-rich success story, or does not, and still becomes a case study. Behind closed doors, risk models quietly shift. If Mars will be far worse with no quick abort and no rapid resupply, doesn't it make sense, some will argue, to accept higher levels of danger on Artemis now, while rescue is at least theoretically possible? It is a cold utilitarian logic. And it is pretty disturbing. During the lunar night, surface temperatures in permanently shadowed regions can drop to approximately minus 230 degrees Celsius, cold enough that carbon dioxide freezes solid. At these temperatures, conventional lubricants like grease become brittle. Mechanical seals fail due to differential thermal contraction, and even titanium alloys experience significant brittleness. A habitat heating system failure lasting more than 4 to 6 hours could cause mechanical failures that cannot be reversed even after reheating. At what point does exploration cross the line into experimentation on human limits? And when that line finally blurs in the gray dust near the South Pole, who exactly gets to decide how far across it Artemis is allowed to step next? That thin line is not just philosophical. On the moon, it is literally being sandblasted away in silence. Unlike Earth, the moon has no air to act as a shield, no blanket of atmosphere to burn up the constant drizzle of tiny rocks and metal fragments that hit the planet every day. Out there, every grain of cosmic debris arrives intact, slamming into the surface, and anything sitting on it at tens of kilometers per second. It never stops. There is no storm and clear sky cycle, only a permanent, invisible shooting gallery. The thing is, most of these projectiles are smaller than a grain of sand. They are almost weightless by human standards. But at 20, 30, even 70 kilometers per second, each one carries staggering kinetic energy. A particle that would disappear in a harmless streak of light in Earth's upper atmosphere can, on the moon, behave more like a microscopic bullet. It can pit aluminum, shatter thin glass, and punch through exposed wiring or tubing. In other words, something that would make a pretty meteor in a summer sky becomes a silent, armor piercing round aimed at life support. Apollo hardware came back from just a few days on the surface with visible pitting and scars. Artemis systems are expected to sit there for weeks, months, eventually years. The scary part is that the longer something stays, the more chances the statistics have to catch up with it. NASA and its partners are not ignoring this. Habitats are designed with multi-layer walls that act like high-tech bulletproof vests. Thin outer plates break up incoming particles, inner layers catch the fragments, and pressure shells sit behind that. Plans call for piling local regolith into berms around modules, using the moon's own dust as a crude shield. But here is where things get uncomfortable. None of that really protects the fragile, exposed systems that cannot be buried. Radiators must face space to dump heat. Solar panels must see the sun. Antennas must stare into the black to talk to Earth. Those surfaces spread out over tens or hundreds of square meters are what the micrometeoroid environment sees first. Imagine an Artemis habitat running normally. Outside, a thin line carries coolant from a pump unit through an external loop, across a radiator, and back inside. It is just a metal tube, a few millimeters thick. One random impact, too small to notice, in real time, punches a pinhole through it. At first, nothing looks wrong. Then the coolant starts to leak, drop by drop, into vacuum. Temperatures inside the loop creep upward. Electronics run a little hotter. A safety margin quietly disappears. Hours later, maybe a day, sensors finally trip alarms. Systems throttle back to protect themselves. Power output falls. Life support has to choose what to prioritize. What would have happened if that line had fed a critical pump or a data backbone instead of a secondary radiator? The result was already decided the moment the particle hit. The humans inside only discover the verdict much later. For Artemis crews, this is the background condition of existence. A constant random bombardment from projectiles they cannot see, cannot hear, and cannot predict. The incredible part was always that most missions survive untouched. Future astronauts will have to trust that the statistics, for a while longer, stay on their side. And if that sounds unsettling for a short lunar stay, it becomes something very different when the plan shifts from visiting the moon to actually living there. A thin metal wall, a few centimeters of regolith, and a stream of electrons in a cable. That is all that stands between an Artemis crew and the kind of cold that ends everything quietly. Because once a lunar outpost stops making power, it stops being a habitat and starts becoming a freezer. On the surface, almost everything that keeps people alive is tied to electricity. The air they breathe runs through pumps and scrubbers. Heating and cooling units constantly fight the brutal swing between sunlit heat and shadowed cold. Communications arrays push signals across 384,000 kilometers, while interior lighting keeps circadian rhythms from drifting into chaos. Even the science depends on it. Seismometers, spectrometers, drills, and cameras all draw steady current. Outside, mobility systems, pressurized rovers, cranes, robotic arms, drink power to move cargo and humans across jagged terrain. In other words, the entire idea of a base on the moon is really an electrical system with people living inside it. The scary part is that the lunar South Pole is one of the worst places to lose power. The sun there never climbs high overhead. It just skims the horizon, casting long, knife-edged shadows. Solar panels see low angles, partial illumination, and long periods where nearby ridges block the light completely. For a while, engineers have talked about peaks of eternal light. ridgelines that stay mostly sunlit. But even those are not perfect. Dust hangs electrostatically above the surface and settles on panels. Each landing blasts plumes of razor-fine regolith outward, coating everything in a thin, gray film that quietly chokes off energy. So Artemis designs lean heavily on batteries and possibly nuclear sources, because long, cold intervals in shadow are not optional. They are built into the landscape. Now imagine a failure chain that begins with a routine landing. A lander touches down nearby. Its exhaust kicks up a dense cloud of dust that races ballistically across the site. The result was predictable on paper, but on the ground it looks different. Panels lose a crucial fraction of their output just as the sun begins to dip. Hours later, a single battery module shorts internally. Capacity drops. A software controller, already stressed by reduced input, misreads the situation and starts shedding loads in the wrong order. Here is where things get uncomfortable. Life support stays on, but thermal control is throttled back too far. The habitat begins to cool. Inside, triage starts. Which systems can be sacrificed? Scientific instruments are powered down first, then exterior floodlights, then non-essential computing. The thing is, every choice buys time in one direction while stealing it in another. How cold can the walls get before water lines freeze? How long can food stores tolerate falling temperatures before packaging fails or critical components separate? What would have happened if the next sunrise was 2 days closer? The incredible part was that the crew still has some control. They seal off unused modules to shrink the heated volume. They ration water to reduce load on purification systems. They move batteries physically closer to the warmest part of the habitat, trying to keep chemistry alive just a few degrees above failure. Outside, the regolith is dropping toward temperatures below minus 150 degrees Celsius. Inside, the lights are dimmed to a twilight glow. Fans whisper more slowly. Every display is switched to low power mode. Astronauts huddle in a narrowing island of warmth, breath faintly visible, running numbers on tablets that must stay on but not too long. They are calculating a cruel equation: whether the remaining charge can carry them to the next sliver of sunlight climbing over a distant ridge, or whether this time the sunrise will arrive just a few hours too late. And this is only one way the moon can quietly turn against them. And this is only one way the moon can quietly turn against them. There is another, less obvious threat. It does not come from the sky or the cold, but from the very act of landing and living there in the first place. When a lander fires its engines near the surface, it does more than just slow down. Its exhaust slams into the ground and turns the soil into a weapon. The gentle gray powder seen in Apollo footage becomes a storm of razor-edged grains, accelerated to hundreds, even thousands of meters per second. In other words, every touchdown is a high-velocity sandblasting event. Nearby equipment, solar arrays, camera lenses, and radiator panels can be pelted by invisible shrapnel. Seals that keep vacuum out can be scoured. Thermal coatings can be stripped. The scary part is, the exhaust plume does not care what belongs to which mission. One bad landing in the wrong spot could quietly cripple systems an entire base depends on. Apollo already hinted at this. Lander pads were blasted clean, and dust coated everything. Artemis will multiply that effect. Larger landers, heavier payloads, more frequent flights. Each descent and ascent near a permanent outpost risks carving new craters, lofting new clouds, and coating old hardware in a fresh layer of abrasive grit. Here's where things get uncomfortable. Over time, repeated operations in the same region could turn the surroundings into a semi-permanent haze of fine particles. On an airless world, those grains do not settle the way they do on Earth. Electrostatic charging can keep them suspended, jumping, clinging to surfaces and suits. Filters and airlocks will help, but nothing is perfect. Dust will ride in on fabric, in joints, under boots. It'll work its way into bearings, valves, and hinges. For a while, systems will shrug it off. Eventually, friction increases, seals wear, and microscopic cuts in lungs and eyes become a real medical problem. The base will be breathing its own pollution. Then there's contamination in a different sense. Rocket exhaust is not just hot gas. It leaves chemical byproducts embedded in the soil and frozen into nearby ice. Human waste, leaked fluids, and trace gases from habitats slowly bleed into the local environment. For scientists trying to study pristine water ice in permanently shadowed craters, the result was always supposed to be a clean record of the early solar system. Now that record risks being overwritten by exhaust plumes and plumbing leaks. Every new rover track, every drill hole, every small reactor or fuel depot adds another possible leak point. The outpost becomes less a clean experiment and more a fragile, self-made ecosystem, where one unnoticed spill can migrate through the regolith and appear months later in a sampling well. The incredible part was that this is exactly what progress looks like in space. More hardware, more activity, more risk. But what would have happened if, in trying to tame the moon, Artemis slowly builds a man-made hazard zone around its own foothold, one mission at a time? The disturbing question is what that hazard zone looks like after decades, and what else might be trapped inside it, waiting for an accident to set it loose. For a while, everything looks fine. The readouts stay green. The pumps keep humming. The lights inside the Artemis habitat glow like a tiny city in the darkness near the lunar South Pole. The scary part is that the most dangerous changes are the ones that do not announce themselves at all. Every lunar day-night cycle, hardware is forced through brutal swings in temperature. Metal contracts in the cold, expands in the heat, and then does it again and again for months. It feels like routine. In other words, it is slow mechanical fatigue disguised as normal operation. Insulation that arrived on the moon pristine begins to develop microscopic cracks. Radiation quietly breaks chemical bonds in plastics and circuit boards. Lubricants in bearings and valves outgas, thicken, or migrate away from where they are needed. The result was never a dramatic snap or explosion at first. It is a motor that needs a little more current, a hinge that resists just a bit, a seal that leaks a few more molecules per second. Early Artemis hardware is designed with lifetimes stamped into the paperwork. So many thermal cycles, so many hours of pump operation, so many charge-discharge loops for a battery. The thing is, the long-term plan assumes these limits can be stretched, that systems can be refurbished or extended on-site without constant resupply from Earth. Here's where things get uncomfortable. Astronauts are not living in a calm laboratory. They are running experiments exploring permanently shadowed craters, dealing with abrasive lunar dust that grinds into hinges and suit joints. At the same time, they are expected to notice a hairline crack in a pressure fitting, hear a slightly irregular whine in a coolant pump, or recognize that an oxygen recycler is taking a few seconds longer to spin up. They had no idea on Apollo how much harder this becomes when missions last weeks instead of days. Inspection turns into a psychological burden. Is that noise new? Is that reading drifting? Or is it just nerves after too many hours in a confined metal shell? Imagine a high demand period, a long EVA into deep shadow near the South Pole, where temperatures can drop below minus 200 degrees Celsius. Power draw spikes as heaters fight the cold. A battery that has lost just 10% of its capacity now runs closer to empty than expected. A coolant pump, its efficiency shaved down by wear, can no longer move quite enough fluid. A small valve made sticky by degraded lubricant and dust responds a fraction of a second late. Individually, none of these are catastrophic. Together, under stress, they can push a life support loop into the red in minutes. The incredible part was how often, in past missions, luck and human improvisation pulled systems back from that edge. On the moon, though, there is no convenient replacement store just over the horizon. When components wear out faster than the spreadsheets predicted, the choices shrink to risky field repairs with limited tools, or an early evacuation through a hostile environment. It is pretty disturbing to ask, what would have happened if the degradation shows itself only when the way home is already closing behind the crew? On Apollo, there was always a comforting phrase in the background: we can come home early. For Artemis, that sentence starts to fall apart the moment the landing legs touch the dust. During Apollo, abort was brutal but simple. Fire the engine, turn for home, splash down in the ocean a few days later. The spacecraft was a single, tightly coupled stack. In other words, if the mission died, everything died together, and the crew rode the same metal shell all the way back. Artemis does not look like that. It is a web, a surface habitat, power systems spread across the regolith, pressurized rovers, caches of tools and samples, and a lander that might not even be the same vehicle that brought the crew from Earth. The scary part is that in this kind of architecture, abort becomes a slow, messy negotiation with the environment. Once a crew is living on the surface, ending the mission early is no longer just about climbing a ladder and lighting an engine. It means deciding what to abandon in place, what to power down safely so it does not become a future hazard, and what vital experiments will be frozen midstream. Do they leave a half-filled oxygen tank connected to a buried line? Do they shut down a nuclear power source in a hurry and hope it behaves? Timing becomes its own trap. Launching from the moon still has windows. The ascent needs the right alignment with the orbiting return vehicle, with Gateway, with the trajectory back to Earth. If a life support system starts to drift toward failure, the result is a disturbing calculation. Leave too early and strand critical infrastructure, or stay long enough to fix what is breaking and risk missing the safest departure corridor. Here's where things get uncomfortable. Imagine the lander has taken a micrometeoroid hit, or a valve is behaving strangely. The engines test out as marginal. Engineers on Earth see worrying data, but no obvious smoking gun. Do the astronauts launch in a compromised vehicle, knowing that any instability during ascent could mean instant loss? Or do mission controllers plan a rescue lander that might not arrive for weeks, maybe months? For a while, Apollo could rely on the idea that there was always another Saturn V on the ground. Artemis does not have that luxury. As infrastructure grows, some expeditions may be designed from the start with no rapid return path at all. Instead, the safety net is redundancy. Extra suits, extra scrubbers, multiple habitats, spare parts scattered across the landscape, and the expectation that problems will be solved in place. The thing is, that flips an uncomfortable switch. There will be scenarios where go is actually safer than abort, where pressing deeper into the mission, profile offers more options than trying to run. And somewhere on the moon, during some future Artemis crisis, Scientists and flight directors will have to answer a question that is pretty disturbing. At what point does coming home become the most dangerous choice of all? That question only matters if the systems stay alive long enough for anyone to make a choice. Because on a lunar base, collapse rarely arrives as a single dramatic failure. It seeps through a web of dependencies, one small glitch at a time, until the entire habitat is hanging by a thread. In an Artemis outpost, almost everything is chained together. Power from solar arrays or nuclear units feeds batteries. Those batteries run life support. Life support depends on cooling loops to keep electronics and air processing hardware within a narrow temperature range. The cooling loops dump heat into external radiators. Those radiators face vacuum, extreme cold, and a constant mist of razor-fine lunar dust. The thing is, if one link in that chain slips, the result is rarely isolated. Imagine a routine software update pushed to the power management system during a quiet lunar night. For a while, nothing looks wrong. Numbers drift, but stay within limits. Then the update mismanages battery charging, driving them slightly harder than planned. They warm up, sensors register the change, and the habitat's cooling system responds by ramping up flow to pull the extra heat away. Here is where things get uncomfortable. The coolant pumps were already working near their design limit because dust has been slowly fouling the external radiators, insulating them grain by grain. To compensate, the system has been quietly pushing more fluid more often. The new thermal load from the overcharged batteries tips it over the edge. A pump begins to cavitate, then stalls. Flow drops. Hotspots form in the life support racks. One of the first casualties is the CO2 scrubber stack, where air must move continuously across chemical absorbers to keep carbon dioxide from building up. The scrubbers trip offline to protect themselves from overheating. Inside the habitat, the air is still breathable, but the partial pressure of CO2 starts to rise. The crew sees high CO2 alarms, not pump cavitation messages. Under stress, with headaches and growing fatigue, they chase the symptom. They swap scrubber cartridges, reroute ducting, even consider scrubbing the air using emergency lithium hydroxide canisters. The scary part is, the underlying cause stays hidden in a tangle of telemetry and software logs. Should they reboot the power controller that started all of this? Cycling power might reset the faulty logic, but it also risks corrupting data, dropping communications, or freezing valves in unknown positions. Leaving everything running risks permanent damage to the batteries and pumps, turning a recoverable software error into a hardware death sentence. On the moon, there is no spare habitat. The incredible part was that Artemis planners anticipated chains like this long before any crew arrived. In high-fidelity simulations, engineers stack failures on top of each other, watching how a single overlooked dependency can push a base from annoying anomaly to prepare for evacuation in hours. It is pretty disturbing, but it is deliberate, because the real question is not whether a glitch will happen. It is what would have happened if no one had traced the first weak link in time. Those stacked failures assume something important, that the humans in the loop notice the first one. But what happens when the weak link is not a sensor or a seal, but a tired hand hovering over the wrong switch? Artemis crews will live inside, demanding timelines that leave very little slack. Long EV, as in stiff suits, hours of habitat maintenance, science tasks that cannot be delayed, mandatory exercise to keep muscles from wasting away, constant reporting, and the never-ending background chore of monitoring life support. All of this packed into days where the crew is small and the checklist is not. For a while, adrenaline will carry them. New landscapes, first footsteps in regions no human has ever seen. The incredible part was how long that worked during Apollo. But Artemis is designed to last longer. Multi-week stays, repeated sorties into shadowed terrain. The thing is, human attention does not scale the way mission planners might like. Sleep will be a problem. It always has been in space. Artificial day-night cycles, alarms in the middle of rest periods, schedule shifts to match orbital passes or communication windows. Add stress, add the monotony of repetitive system checks, and the result was always the same on earlier missions. Attention starts to fray at the edges. Here is where things get uncomfortable. In that state, misreading a gauge is easier. Skipping a single line in a procedure is easier. A hand reaches for a familiar toggle and lands one row too high. In a pressurized habitat on Earth, that might just trip a breaker. In a lunar base, it might isolate an oxygen tank. History has already shown how close this can get. During Apollo 13, a simple procedure change and an overlooked wiring vulnerability turned a routine tank stir into an explosion. On Mir and the ISS, there have been incidents where valves were left in the wrong configuration, or alarms were misunderstood for crucial minutes. The scary part is that those crews had relatively quick return options. Artemis astronauts near the lunar South Pole will not. In other words, the margin for recovery shrinks. A misset valve for a water recycling loop might not be noticed until ice forms in the wrong line. An incorrectly acknowledged suit alarm during an EVA could mean a slow, unnoticed leak in a place where rescue is hours away, in a terrain that is permanently dark and far below minus 200 degrees Celsius. Layered on top of this is a quieter pressure. Every action, every hesitation, every near mistake will be recorded, time-stamped, and dissected by mission control and by scientists studying human performance. Knowing that can create a different kind of stress. Second guessing in the middle of a critical sequence. Fingers hovering over a switch for one heartbeat too long, or not long enough. The scary part is that even perfectly designed systems can be defeated by that moment. A checklist can be flawless on paper and still fail in the hands of an exhausted operator at hour 19 of a long day. Artemis will not just test hardware in extreme cold and radiation. It will test how far tightly scheduled, heavily observed humans can be pushed before the line between routine operation and irreversible error quietly disappears. And if that line moves in ways planners did not predict, the next threat does not have to come from a micrometeoroid or a solar storm. It can begin with a single, very human click in the wrong direction. It starts with a click, not an explosion, not a warning siren. Just the quiet moment when a voice on the loop cuts off mid-sentence and does not come back. Artemis depends on a fragile web of connections. From the lunar surface, antennas on the lander, and the base beam signals up to orbiting platforms and relay satellites. Those, in turn, route data either through the planned gateway station or directly back to giant dishes on Earth. In other words, surface-to-orbit links, relay nodes, and Earth-based receivers all have to stay perfectly aligned for the illusion of constant presence to hold. The thing is, every part of that chain lives in an environment that wants it dead. A micrometeoroid no bigger than a grain of sand can punch into a high-gain antenna feed and detune it just enough to wreck the signal. A software update on a relay satellite can crash at the wrong millisecond and leave the spacecraft stuck in a reboot loop. A power controller on the surface can trip during a shadowed traverse, leaving dishes frozen in the wrong direction while batteries sag. Here is where things get uncomfortable. None of those failures has to be dramatic. A tracking dish on Gateway can simply lag behind during a critical attitude maneuver. The result is a surface crew stepping out of a rover near the lunar South Pole, relying on that link and hearing only static. No orbit, no Earth, just a dead loop in the middle of an already dangerous task. Mission rules will assume this happens eventually. Crews will carry pre-planned procedures, printed checklists, and time-tagged actions that continue even if every voice from home disappears. For a while, that works. They follow the script, complete steps, and trust that someone, somewhere, is recording their telemetry and will call back in. But what happens when the emergency does not match the script? Imagine a slow leak in the habitat, alarms starting to climb, and no one on Earth answering. The scary part is that Artemis is intentionally pushing into regions where rescue is not just hours away, but days. There is no quick return to Earth, no immediate expert in a headset talking through options second by second. Psychologically, true silence is different from delay. No reassuring background murmur from Houston, no calm voice from Gateway. Only the hiss of suit fans, the thump of a heartbeat in a helmet, and the knowledge that, at this exact moment, no one knows what is happening on the surface. They had no idea if the problem is local or systemic. The incredible part was always how much courage earlier crews drew from a simple crackling radio call across the void. Take that away, and the moon becomes something else. Not a distant outpost, but a sealed room with no outside line. Now reverse the picture. On Earth, the big antennas keep tracking, but the screens stay flat. No video, no audio, just stale data from minutes before the blackout. In a habitat that is still pressurized, with life support still running, a living crew stares at equally dead displays, wondering if Earth was lost to a storm, a war, or a glitch. Both sides are intact. Both are operational. And both are suddenly alone. It is a fully functional base, a breathing team, and a silent planet, each convinced the other might already be gone. And if that silence stretches from minutes into hours, the next decision Artemis planners fear most is the one that comes next. What does a crew do when the only way to break the quiet is to risk everything? A stranded crew on the moon is terrifying enough on its own. The disturbing part is how quickly that scenario stops being only a technical problem and becomes a political one. Artemis is not just a scientific program, it is a geopolitical project, wrapped in timelines, milestones, and international promises that sit on briefing slides in Washington, Paris, Tokyo, and beyond. Launch dates are announced years in advance. Flags are painted on hardware. Partnerships are signed. In other words, the schedule itself becomes a kind of life support system that everyone is afraid to unplug. The thing is, rockets and habitats do not care about election cycles. Valves stick when they want to. Cracks appear where they should not. But on the ground, there is a calendar that keeps moving. And behind it are budgets that must be justified. If a mission slips too far, funding can evaporate. So the scary part is that the pressure to be on time can quietly push decision makers toward accepting risks that would look unacceptable in isolation. Here is where things get uncomfortable. Most of those risks are not dramatic countdown stopping failures. They are probabilistic. A seal that is slightly out of spec, a software anomaly that only appears once in 1,000 simulations, a radiation model that assumes the next solar cycle will be average. Each one on its own can be argued away. Together, they form a statistical minefield that is hard to see and even harder to sell to the public. Agencies are supposed to be transparent. They publish risk matrices, loss of crew probabilities, safety reviews. But the result was never meant for a headline. Mission has a 1 in 70 chance of killing its crew is technically honest and politically lethal. So the language softens. Numbers are buried in dense reports. And for a while, almost no one outside the inner circles asks what would have happened if the dice rolled differently on a previous flight. The incredible part was that this tension has always been there. Apollo 8 went to lunar orbit with a rocket that had never flown crew before. The shuttle flew with known foam shedding until Columbia. Now Artemis carries international prestige and commercial contracts on its back. Cancel a launch after a minor anomaly, and partners may question the entire architecture. Fly anyway, and a single accident could unravel decades of diplomatic work in one awful morning. Behind closed doors, another calculation appears. Hardware will be lost. Landers will crash. At some point, a crew might not come home. It is rarely said out loud, but it is implicitly priced into long-term exploration. Pretty disturbing given that each number on a risk chart corresponds to real faces, real families, and a real emergency call in the middle of the night. So the question hangs over Artemis like a second invisible countdown. Does the collective appetite for dramatic victories on the moon truly match the quiet statistical reality of what those victories demand? Or is the risk budget being written under the assumption that the worst case scenario will always stay hypothetical right up until the moment it doesn't? Because the next time a crew is ordered to light an engine with marginal data, the decision will not just be about engineering. It will be about how much failure an entire civilization is willing to accept in exchange for one more footprint in the dust. But there is another variable in that equation that no flight director can fully control: other people. For most of the space age, the moon was empty. Apollo left flags, footprints, and a few dead machines. Then the surface went quiet again. Artemis changes that, but not alone. The thing is, almost every major space power now has its eyes on the same gray rock. NASA's partners under the Artemis Accords are planning their own landers and surface infrastructure. China and Russia are talking about a joint lunar base. India, Japan, South Korea, the UAE, and others are funding missions. Private companies are building commercial landers, prospecting rovers, even early concepts for mining systems. In other words, the moon is about to become crowded. On paper, this looks like progress. More science, more redundancy, more capability. But here's where things get uncomfortable. None of this activity is happening in a vacuum, politically or physically, and the scary part is how easily one mission's success could become another mission's emergency. Imagine two landers targeting nearby regions at the lunar South Pole. One is a crewed Artemis mission, the other a commercial cargo flight delivering hardware for a future base. A minor navigation error shifts the second vehicle's descent path. Its engine scours the surface, blasting plumes of dust and gravel at high velocity across the local terrain. On Earth, exhaust disappears into air. On the moon, there is no air. Dust grains follow ballistic arcs for kilometers. Scientists already worry that a single badly placed landing could sandblast nearby habitats, solar arrays, or radiators. The result was predicted in models for years: contaminated instruments, abraded visors, clogged joints. But what would have happened if that plume intersected an active EVA or a fragile life support line? Interference is not just physical. Landers, rovers, and bases all need radio links, navigation beacons, and relay satellites. Uncoordinated frequencies or overpowered transmitters can drown out weaker signals. A distant mining operation, running heavy drills and power systems might generate electromagnetic noise that masks a distress call from a stranded crew. Then there is the ground itself. One program wants to drill for ice in a permanently shadowed crater. Another has placed a habitat on the rim, relying on that ice as a long-term resource. Aggressive excavation could destabilize the regolith, undercutting foundations or triggering slow, creeping subsidence beneath someone else's outpost. It could also stir up volatile rich layers and contaminate pristine deposits that scientists have waited decades to study. All of this unfolds under a thin legal framework written in an era when only two superpowers mattered. The Outer Space Treaty forbids national appropriation, but it says nothing clear about de facto safety zones around critical infrastructure. What happens when one nation declares a keep-out area around its ice extraction site and another refuses to recognize it? Now add real lives to that map. An injured astronaut from country A needs shelter in a habitat run by country B. But relations on Earth have deteriorated. There are disputes over orbits, sanctions, military satellites. Does the hatch still open without question? The incredible part was that for a while, international cooperation in orbit seemed almost immune to terrestrial politics. The International Space Station kept flying through wars and crises. Yet the moon is different. It holds resources, strategic high ground, and symbolic power. Any incident, a collision, a radio blackout, a disputed landing, could be framed as negligence or worse, as sabotage. Emergency rescue on the lunar surface will already be on the edge of what is technically possible. Delayed launches, narrow transfer windows, limited fuel margins. Add mistrust, conflicting territorial claims, or accusations of interference, and the window for help narrows even further. And this is where the picture of a busy international moon becomes pretty disturbing. The environment is hostile enough on its own. But the most dangerous thing on the moon may not be the vacuum, the radiation, or the dust. It may be other humans operating under different rules, different goals, and very different ideas about how much risk is acceptable in the dark. For NASA, that question about acceptable risk does not end at the moon. It points somewhere much farther away, to a place that makes even a lethal, disputed South Pole outpost look almost safe. Officially, Artemis is not the finish line, it is the rehearsal. The program is described as a stepping stone, a way to prove that humans can live off Earth for weeks at a time, operate complex machinery in deep cold and darkness, and survive in a place where every breath depends on hardware. In other words, the moon is being turned into a nearby test site for something worse. That something is Mars. A crew going to Mars will not be 3 days from home. They will be months away, locked into a trajectory that cannot simply be reversed if something goes wrong. The trip itself passes through regions of space with harsher radiation than any Apollo crew ever saw, without the partial shelter of Earth's magnetic field. Communication delays stretch from several minutes to more than 20 one way. A real-time conversation becomes impossible. Compared to that, a moon mission starts to look almost forgiving. Almost. Here is where things get uncomfortable. When mission planners look at hazards on the moon, radiation, dust, life support failures, they also ask a disturbing follow-up. Is this avoidable on Mars or not? If the answer is no, if a threat is baked into the physics of interplanetary travel, there is intense pressure to face it at the moon first, where a rescue is at least conceivable. The scary part is that this logic pushes Artemis towards the edge on purpose. Lunar dust is razor sharp and electrostatically charged. It clings to suits, grinds into seals, infiltrates air systems. On Mars, abrasive dust storms will be worse and last longer. So Artemis hardware has to be driven until filters clog, joints seize, and seals begin to leak, just to learn exactly where they fail. The result was never meant to be a clean, flawless record. The result is data about how and where things break. The same thinking applies to human bodies and minds. Artemis crews will live for weeks in confined habitats, stepping outside into a vacuum where a torn glove could mean death in seconds. For a while, scientists will watch how sleep, decision-making, and stress change when a person spends that long knowing that a single unnoticed crack in a line or valve could quietly kill everyone inside. The incredible part was that this is framed not as cruelty, but as responsibility. Better to trigger a controlled failure 3 days from Earth than discover the same weakness halfway to Mars with no turning back. Which leads to a final, pretty disturbing question. How far will Artemis be pushed in the name of making Mars survivable? And what happens if, one day, the rehearsal stops feeling like a rehearsal at all? Inside NASA, the rehearsal continues in places the public will never see. On paper, Artemis is a path to a sustainable lunar presence. Behind closed doors, it is also a spreadsheet of ways human beings can die on the way to that goal. Mission designers do not start with slogans. They start with numbers. Every major system, from a spacesuit bearing frost at the lunar South Pole to a life support loop humming inside a pressurized rover, is fed into probabilistic risk assessments. In other words, thousands of potential failure modes are mapped, weighted, and combined into branching trees of what would have happened if one more thing went wrong. The scary part is that many of those branches are never meant for a press conference. For a while, Apollo engineers did this with slide rules and intuition. Artemis planners have full digital twins of vehicles, habitats, even human bodies under stress. They run simulations of multi-system failures in the 2-week lunar night, when solar power collapses and batteries and fuel cells are the only barrier between a sleeping crew and vacuum-cold metal. Here is where things get uncomfortable. Known hazards become templates for unspoken scenarios. Take a power failure that knocks out heating in a south polar outpost. Now layer in a comms glitch during a solar storm, a stuck airlock seal, and an astronaut with a slow internal bleed after a fall on the regolith. The result was not just a single emergency, but competing ones. Save power, stabilize pressure, stop the hemorrhage, all while Earth hears only fragments. Statistically, based on historical spaceflight data, missions with multi-week durations in extreme environments show a cumulative fatality risk of approximately 1 to 3% per mission for crews operating in confined spaces with limited rescue options. With Artemis planning 20 to 30 missions in the 2030s to 2040s, baseline probability models suggest a 20 to 50% likelihood of at least one crew fatality during this phase of the program, assuming no major design changes or technological breakthroughs in autonomous rescue systems. Scientists infer some of these internal nightmares from the way NASA publicly categorizes outcomes. Loss of mission if objectives fail but the crew survives. Loss of vehicle if the ship is gone but lives are not. Loss of crew when the line is crossed. Behind each label sits a family of simulations. A suit puncture during a critical ascent burn. A lander engine out just meters above jagged terrain. A medical code blue in one bunk while another astronaut is outside, tethered mid-repair. The incredible part was never the technology itself. It is the way planners work backwards from those worst boxes on the chart, shaving probabilities down until they are politically acceptable. Not zero, just low enough. And some branches refuse to be tamed. Micrometeoroid hits that arrive without warning, lunar dust infiltrating seals until one fails at the wrong second, psychological breaks after months of darkness at the pole. These are listed, modeled, and, in some cases, left with only partial mitigation. Extra armor here, redundant sensors there, a checklist that might buy minutes, not hours. It is pretty disturbing to realize that, on certain pages, the best case note is simply, crew unrecoverable, but cause understood. So a final question hangs over Artemis, unprinted in any brochure. If the full list of ways these missions could end in tragedy were laid out in front of the world, would humanity still want to go? Those pages are only abstractions. What happens when the ink turns into air hissing out of a wall, a suit, or a human body? Imagine an Artemis habitat during lunar night. Outside, the regolith is more than minus 170 degrees Celsius, the sky perfectly black. A grain of rock no bigger than a sand particle arrives at tens of kilometers per second. It punches through a thin section of the habitat shell and keeps going. No alarm, no dramatic bang, just a pinhole. For a while, the only evidence is a pressure drop so small it hides inside sensor noise. The scary part is that the first symptom the crew might notice is not the leak itself, but the life support system working harder. CO2 scrubbers run hot, fans spin faster, filters saturate earlier than expected. Here is where things get uncomfortable. By the time someone asks why the scrubbers are failing early, the leak has been quietly bleeding air for hours, maybe days. The crew has to decide, attempt an emergency inspection and patch in the middle of a 2-week darkness cycle when external temperatures and power margins are at their worst, or start shutting down non-essential systems and prepare the lander for a possible evacuation. What would have happened if a single additional sensor had flagged the pressure drift earlier? Or if the patch kit was designed for gloved hands in hard vacuum instead of shirt sleeves inside? In other words, the difference between a tense repair story and a habitat slowly becoming uninhabitable could be a few grams of extra hardware. Now shift to an EVA near a shadowed crater at the South Pole. The terrain is jagged, the lighting brutal. Blinding glare on one ridge, absolute blackness a few meters away. An astronaut follows a planned route, relying on suit nav, visual landmarks, and line of sight to the lander. Then dust gets kicked up. A visor coating fails. A navigation glitch freezes the map. They crest a small rise and the lander disappears behind a ridge. For a moment, there is only static gray slopes and a suit clock counting down remaining oxygen. The result is a choice with no good options. Follow a risky, steeper path that should lead directly back, but crosses unknown boulders and potential crevasses, or stay put and hope the crew can triangulate a position from intermittent suit telemetry. Every minute spent debating is another percentage point off the oxygen gauge. The incredible part was that in Apollo, line of sight and short walks made this almost unthinkable. Artemis deliberately stretches those margins. Finally, consider a small pain in the abdomen on day 9 of a surface mission. At first, it is dismissed as stress or dehydration. Hours later, the pain localizes, fever rises, nausea starts. Appendicitis? Gallstones? On Earth, this is an ambulance ride and a routine surgery. On the Moon, there is no surgeon, no operating room, and only a limited pharmacy. Again, small differences matter. A slightly broader drug kit, a portable ultrasound that can resolve a swollen appendix in one clear image, a pre-positioned return vehicle with faster turnaround. Each one shifts the curve away from first death on the moon and toward terrifying case study in a medical journal. None of these scenarios are wild science fiction. They are straight line extrapolations from known hardware, real environmental data, and the brutal constraints of distance and time. For Artemis planners, the disturbing reality is that every one of these paths has to be walked in detail, step by step, long before the first crew walks down a ladder. And the question that lingers is simple. How many of these near-miss futures can be engineered away before the missions themselves stop being possible? Some of those near-miss futures stay on paper. Others are tested in dust, vacuum, and darkness. Because Artemis is not just about planting flags. It is about extracting knowledge from a place that does not care if anyone survives long enough to use it. On paper, the benefits look almost irresistible. Detailed maps of lunar geology and history that lock down how the moon formed, when its volcanoes died, and how often it was hit by world-ending impacts. In other words, a clearer record of what has already tried to kill Earth and what might try again. Artemis also promises something far more practical, learning to extract and use space resources, especially water ice buried in permanently shadowed craters near the South Pole. Turn that ice into air, drinking water, and rocket fuel, and the moon stops being a dead rock and becomes a gas station, a laboratory, and a training ground all at once. For life support engineers, the result was a once-in-a-generation opportunity. Closed-loop systems that recycle air, water, and waste for weeks or months in a small, sealed habitat. Radiation shielding that has to work when solar storms hit without warning. Habitat designs that survive brutal temperature swings, from blistering sunlight to minus 200 degrees Celsius shadow. The scary part is that the same technologies needed to keep a crew alive in that environment are exactly the ones needed to make Earth more resilient, more efficient recycling systems, smarter power management that can ride out blackouts, disaster response techniques for when infrastructure fails and help is far away. Psychologists see another layer. Artemis crews will live for a while in extreme isolation, under constant awareness that a thin shell of metal and plastic stands between them and vacuum, studying how stress, fatigue, and confinement reshape decision-making could feed back into everything from submarine operations to emergency medicine on Earth. Here is where things get uncomfortable. Some breakthroughs only appear when systems are pushed until they bend or almost break. A life support glitch that forces a crew to improvise a fix. A habitat leak that is contained just in time. An incident that is non-fatal but reveals a hidden weakness no simulation ever caught. Engineers will mine those near misses for data. The result was always the same lesson in previous programs. Real hardware, in real conditions, fails in ways no one predicted. They had no idea until it happened. And beyond even that, the possibility of becoming a multi-planet species, not as a fantasy, but as a hedge against global catastrophe. If something like the 1054 supernova happened closer, or a 2012 scale solar storm hit head-on, where would humanity stand if there were no footholds off-world? The incredible part was that Artemis is designed as that foothold and as a rehearsal for something even more dangerous, Mars. Every risk accepted on the moon is a down payment on future missions that will be months from home with no quick return. So the bargain is stark. Knowledge, capability, and a shot at long-term survival in exchange for sending people into an environment that will eventually exploit every oversight. Knowing the risks, is that bargain worth it? And who exactly gets to decide how much danger is acceptable in the name of discovery? The disturbing part is that the bargain cannot be fully calculated in advance. For Artemis, there is no simulation that can perfectly stack every variable that matters. Vacuum, 1/6 gravity, razor-edge dust, deep cold in permanent shadow, weeks of confinement, months of cumulative radiation. Each piece can be modeled on Earth. The combined environment, operating on human bodies and machines for months or years, cannot. The thing is, this uncertainty is not new. Aviation in the early 1900s looked safe on paper, right up until wings snapped in midair because designers had underestimated turbulence. Polar expeditions left with careful plans and detailed maps, then vanished into whiteout and thin ice. Early spaceflight, from Apollo 1's cabin fire to Soyuz 11's depressurization, revealed lethal design gaps only after crews were already dead. In other words, safety advances usually followed the tragedy, not the other way around. Engineers learned which valves needed redesigning only after they stuck at the worst possible moment. Mission planners learned which procedures were missing only after someone tried to follow them and found nothing there. The result was a brutal feedback loop. Progress paid for in blood, then used to prevent the next disaster. Artemis, despite its layers of modern engineering and caution, sits directly in that same pattern. Missions will push into the lunar South Pole, into terrain no astronaut has ever walked, where temperatures and shadow plunge below -200 degrees Celsius and sunlight never arrives to help. Habitats will have to hold pressure for weeks. Life support systems will run non-stop. For a while, everything may look stable. But the scary part is that long-duration stress reveals failures that short missions never show. A micrometeoroid that would have missed during a 3-day stay might puncture a habitat wall in week 3. Lunar regolith that was just an annoyance during Apollo could, after months of grinding into seals and lungs, become a genuine medical and mechanical threat. What would have happened if Apollo crews had stayed for 90 days instead of 3? Here is where things get uncomfortable. Artemis is not just exploring the moon. It is experimenting on the future, on the limits of human endurance in a place where a torn suit means death in seconds. On the edge of technology that will later be pointed at Mars, where no quick return is even possible. On ethics, as decision makers quietly decide how much chronic radiation, isolation, and psychological strain counts as acceptable. Astronauts will live with the constant awareness that a single cascading failure, air leak, power loss, medical emergency, could play out over hours, with help days away and no rescue launch on the pad. Scientists will study their bones, brains, and blood for subtle damage, knowing that some consequences may only surface years later. The incredible part was always the same in earlier eras. The line between calculated risk and unacceptable sacrifice only became obvious in hindsight. After the accident report, after the memorials, Artemis will be no different. The question is, when that first hard lesson arrives on the moon, what exactly will it reveal? And who or what will pay for it? For one person, that hard lesson is not abstract at all. It starts years earlier in a fluorescent-lit training bay in Houston, long before any accident report exists. A potential Artemis astronaut's life narrows into repetition, neutral buoyancy tanks that mimic weightlessness, vacuum chambers that simulate a dead, airless moon, endless runs through failure scenarios where the instruction is simple and brutal. Assume something vital has just broken, and assume no one is coming in time. Day after day, they rehearse what would have happened if an oxygen line ruptures during a spacewalk. If lunar dust infiltrates a seal and refuses to let go. If a micrometeoroid punches a pinhole through a habitat wall while everyone is asleep. The scary part is that the training is not designed to remove the danger. It is designed to find out how close a human can stand to it without falling in. Here is where things get uncomfortable. Behind the simulations and the checklists, there is a private calculation that no mission patch ever shows. On one side, a childhood dream of walking where almost no one has walked, of leaving footprints in the frozen shadows near the lunar South Pole, of contributing data and experience that might eventually carry the species to Mars. On the other, a partner who has already imagined the knock on the door, children who will grow up with a flag and a plaque instead of a parent. In other words, the risk is not a number on a chart. It is a face at the kitchen table. Still, the numbers are there. Quiet, precise, disturbing. So the question is forced. Would a person accept a 1 in 1,000 chance of not coming home? That sounds almost safe until the mind lingers on the word 1. What about 1 in 100 when the odds begin to resemble early spaceflight again? 1 in 50, when each launch starts to feel like drawing from a shrinking deck? At what number does the answer change? And how honest would that answer be if the launch pad were visible through the window? For some, the result was always going to be the same. The chance to step into those permanently shadowed craters where temperatures plunge below minus 200 degrees Celsius and sunlight never touches the ground will outweigh almost anything. They will accept that a torn suit means death in seconds, that a medical emergency on the moon may unfold in real time for family members watching a delayed feed on Earth. The thing is, this is not just about one mission. Artemis is explicitly framed as a proving ground, a place where scientists and engineers learn how human bodies and minds behave when pushed toward the limits required for Mars. The moon becomes a laboratory for survival, and each astronaut is both explorer and test subject. The incredible part was never the rocket or the habitat. It is the decision, repeated in dozens of quiet moments, to keep saying yes. Artemis, beneath the acronyms and hardware, is a chain of personal choices made by individuals willing to stand where almost everyone else only watches, and to accept that, in the darkest parts of the moon, the margin for regret may be measured in seconds. That used to be where the story ended. A small group stepped into danger. Everyone else watched from a safe distance, and then the broadcast cut back to regular programming. Artemis breaks that pattern. These are not one-off flags and footprints missions that vanish into history after a few tense days. They are designed as a sequence, an ongoing presence with launches, landings, cargo runs, and surface expeditions repeating until lunar risk is no longer a rare spectacle, but a background noise in everyday life. The thing is, background noise can still be lethal. A habitat leak on the 7th mission, a suit failure on the 12th, a lander abort on the 19th. Each one plays out in real time, under a level of public visibility Apollo engineers never had to face. The scary part is that the line between historic achievement and live stream disaster is now only a few camera angles wide. During Apollo, grainy television and delayed reports filtered the danger. Artemis will not be filtered. High-definition helmet cams, constant telemetry overlays, social media feeds, And real-time commentary will pull millions of people directly into the tension of an EVA near the lunar South Pole, or a dust storm of regolith kicked up around a landing site. Viewers will watch heart rates spike, hear clipped breathing, and see warning lights flash as they happen. Here is where things get uncomfortable. Public reaction is no longer just emotional. It becomes a variable in the risk equation. A near miss with a micrometeoroid, a malfunctioning life support valve, or a rover crash on a shadowed slope will not only be investigated by engineers and scientists, it will be dissected by commentators, amplified by algorithms, and translated into pressure on politicians who decide whether the next mission flies at all. In other words, attitudes become infrastructure. If a minor incident is framed as a failure, budgets can evaporate. If a serious accident is wrapped in sanitized language, the disturbing lessons might be ignored. The result was clear after past disasters. Public outrage reshaped designs, procedures, even entire programs. With Artemis, that feedback loop runs faster and louder than ever before. Over time, something deeper shifts. As lunar missions stretch from days to weeks, as images of astronauts working in regions colder than minus 200 degrees Celsius become routine, society's baseline for what counts as an acceptable level of risk quietly moves. What would have happened if this kind of normalization had existed before Challenger or Columbia? Would warnings have been heard or drowned out by expectation? Eventually, living off-world may feel less like an expedition and more like an extension of human geography. That is the incredible part, and also pretty disturbing, because once the moon is treated as another place people simply go for a while, the threshold for sending crews even farther, to Mars, to more isolated orbits, will drop. So the way Artemis is described now matters. Honest talk about lethal dust, radiation, and the thin margins of survival prepares the public for the day something goes very wrong on a distant gray horizon. Sanitized narratives do the opposite. They build a fragile confidence that will shatter in the first dark moment just before the next, even more dangerous destination is announced. For a while, Artemis is framed as a return. A new flag, new footprints, new cameras sending back high-definition views of a familiar gray desert. The thing is, that is only the surface story. Beneath the public language about discovery and inspiration, Artemis is being built as something else, a rehearsal for long-term human survival when Earth itself becomes unreliable. Not in a science fiction sense, but in the very practical context of asteroid impacts, runaway climate disasters, and cascading infrastructure failures that could make off-world habitats more than scientific outposts. Here is where things get uncomfortable. Living on the moon for weeks at a time forces engineers to solve the exact problems that a fractured, damaged Earth might face later. Closed-loop life support, power grids that cannot fail, medical care in isolation, and psychological stability in places where stepping outside without a suit means instant death. In other words, Artemis is stress testing the blueprint for refugees that might one day be humanity's only backup. Artemis crews will not just visit the moon. They will try to live there in regions far harsher than Apollo ever touched. Near the South Pole, some craters sit in permanent darkness, colder than minus 200 degrees Celsius, with no direct sunlight and no easy rescue. The scary part is that these are exactly the kinds of environments planners study when they imagine survival colonies after a global catastrophe. What would have happened if Earth's atmosphere were choked by ash, or its power grids crippled for years? The moon quietly becomes the dress rehearsal for that question. Scientists already talk about Artemis as a stepping stone to Mars, but that phrase hides something disturbing. By learning to keep people alive on the lunar surface, mission after mission, the result is a hard data set on whether the species can function as a truly multi-planetary organism, not just for a flag ceremony, but for entire lifetimes spent off-world. If those experiments succeed, the path to permanent human populations beyond Earth stops being hypothetical. It becomes a policy choice. And the incredible part was never the rockets or the landers. It is the scenarios being normalized. Habitat breaches from micrometeoroids, medical emergencies days away from a real hospital, psychological strain in metal rooms where every argument, every mistake, plays out under the constant awareness that a few millimeters of aluminum separate breathing air from vacuum. The same pretty disturbing situations described as edge cases in training manuals may eventually become the daily reality of people born under a different sky. They had no idea during Apollo that fungal colonies would evolve aggressively on Mir, or that cosmic rays would paint eyeball flashes across sleeping astronauts' vision. Now those lessons feed directly into Artemis. Radiation shielding, microbial control, emergency protocols, all refined on a world that was supposed to be a destination, but is slowly turning into a proving ground. The last twist is the most unsettling. In trying to escape the vulnerabilities of a fragile planet, humanity may be exporting them instead, carrying political tension, resource inequality, and biological frailty into every new habitat. The moon might not save anyone from those forces. It might only concentrate them in smaller, more fragile cans of air. And somewhere in the planning documents for the first permanent lunar base, there is an unspoken question waiting for an answer. When the next crisis comes, who actually gets a seat inside? Those seats come with a price tag that is hard to look at directly, because Artemis is not designed to make the moon safer. It is designed to walk straight into the parts that are most hostile to human life. The surface itself is a problem, airless vacuum waiting behind every seal, radiation that slips through tissue and DNA in silence, temperatures that swing from oven to cryogenic freezer, and a layer of razor-sharp dust that never erodes, that clings to suits, grinds into lungs, and chews through metal and rubber over time. The scary part is that Artemis goes closer to all of this than Apollo ever did, pushing into the permanently shadowed craters near the South Pole, where the cold drops below minus 200 degrees Celsius and sunlight never arrives. Inside those habitats, the threats change shape but never really go away. Life support becomes a single point of failure, not a background system. A clogged filter, a leaking valve, or a software glitch in an oxygen loop can cascade into an unlivable cabin in minutes. In other words, the entire mission hangs on pumps, seals, and lines of code behaving perfectly for weeks in a place that offers no backup. Here is where things get uncomfortable. That is exactly when complex repairs, delicate landings, and high-stakes decisions still have to be made. Medical support is no longer a quick medevac and a hospital on Earth. It is a limited kit, partial diagnostics, and a short but very real communication delay with ground controllers. A burst appendix, a stroke, a micrometeoroid wound through a limb. On Earth, those are emergencies. On the moon, the result was always going to be a test of what can be done with what is already there and what cannot. Artemis is a deliberate escalation. Longer stays on the surface, rovers driving into rougher, more fractured terrain, more autonomy from mission control as crews operate beyond constant supervision. The incredible part was never just the technology. It is that mission planners are consciously using the moon as a proving ground to find out what would have happened on a months-long Mars trip, without admitting that some lessons may only be learned through failure. Behind that are quieter calculations, questions about informed consent, about what level of risk is acceptable when the danger is abstract and far away. International partners and private companies competing for landing sites, resources, and prestige. Every design review is effectively a negotiation over how many things are allowed to go wrong before a crew has no way out. It is pretty disturbing how normal this has become inside the spreadsheets. So Artemis becomes a paradox, a program built on humanity's highest aspirations and on an unspoken willingness to send people into an environment that does not care if they live or die. The moon turns into both a beacon and a filter, and somewhere in the shadows near the South Pole, the next question waits. What happens the first time the edge of survivability is crossed and the mission does not come home? That question does not stay on the moon. It comes back to the person watching, sitting in a world that feels safe only because the vacuum outside has not failed anyone yet. So here's where things get uncomfortable. Looking back over these Artemis scenarios, which one stayed in the mind the longest? The slow leak in a habitat wall that no one notices until the alarms start, the razor-sharp lunar dust grinding into lungs and seals, the medical emergency in a base that is 3 days and hundreds of thousands of kilometers from an operating room. Which detail was the most disturbing, and does support for Artemis survive, knowing that this is not science fiction, but the baseline reality of the mission? The thing is, Artemis is not designed to be safe in the way commercial air travel feels safe. It is designed to be survivable at the edge. NASA will send crews into permanently shadowed regions where temperatures fall below minus 200 degrees Celsius, where a torn suit is not a bad day, but a death sentence measured in seconds. If a seat on one of those missions was offered, with every risk explained in unflinching detail, would it be taken? Why or why not? For some, the answer would be immediate. For others, it would change after hearing about radiation storms, about micrometeoroids that arrive without warning, about the psychological strain of weeks in an outpost surrounded by nothing but darkness and rock. The scary part is that human exploration has always depended on a small number of people saying yes anyway. But how far should that yes be allowed to go? Eventually, Artemis will move from concept art to archived history. The question is what role the audience chose to play while it was unfolding. Engagement is not just numbers on a screen. In other words, it becomes part of a public record about how society responded to risk in space. So, if more deep dives into the unsettling realities behind exploration are wanted, if a wider conversation about how humanity chooses to face the darkness beyond Earth feels important, now is the moment. Like, subscribe, and share this video. Turn a private reaction into a visible signal that the full story matters, not just the parts that make good posters. For a moment, ignore the launch pads, the press conferences, and the glossy animations. Return to that first image. An Artemis crew stands near the lunar South Pole, their suit lights cutting thin cones into a darkness that has never seen sunrise. Beyond that narrow glow, everything drops away into a black, airless cold that reaches below minus 200 degrees Celsius. Now, after everything covered in this video, that scene looks different. Every system around them is a potential single point of failure. Each habitat is a pressurized bubble holding back vacuum. Each cable, each valve, Each radiation shield is a quiet bet against a universe that does not care who wins. The scary part is that all of humanity's hope, fear, and ambition in this place fits into a few metal shells and a handful of walking targets in white. Outside, the moon is silent and indifferent. It does not react to heart rate spiking inside helmets or to mission control holding its breath across a 1.3-second delay. It only reflects sunlight, absorbs radiation, and waits. Inside those suits, something very different is happening. Artemis astronauts will walk into regions Apollo never reached, permanently shadowed craters, long stretches of twilight where the sun barely scrapes the horizon. In other words, places where a torn glove or a cracked visor is not a problem to be managed, but a sentence measured in seconds. Here is where things get uncomfortable. Every step deeper into those shadows is also a step taken for everyone watching from Earth. The result was always going to be the same: the moon changing from a distant light in the sky into a workplace, a site of experiments, a training ground for even more dangerous journeys toward Mars. For a while, that transformation will look orderly. Checklists completed, samples collected, data transmitted. But in the background, the real experiment is about how close humans can move to the edge of survival without falling over it. Scientists know more now than any generation before about radiation, dust, and psychological strain. They have modeled what would have happened if a micrometeoroid sliced through a habitat wall, or if a medical emergency unfolded days from home with only limited help from Earth. And still, the plan is to go. The incredible part was never the technology. It is the decision to walk into this with open eyes, fully aware that the moon will not bend its physics for anyone. So the camera pulls back. The Artemis base shrinks to a fragile cluster of lights clinging to the rim of an ancient crater, then to a pinprick on a dead, gray sphere, then to nothing at all, swallowed by the same darkness that surrounds every near miss, every unexplained signal, every disturbing event beyond Earth. What will be waiting in those shadows decades from now? What stories will be told about the first workers on the edge of that abyss and the ones who did not come back? The frame fades to black, leaving only the question of whether the risk was worth what was found out there. That answer, for now, stays off screen. The Artemis program's life support systems are designed with a maximum time to rescue parameter of 72 hours. However, orbital mechanics mean that emergency rescue vehicles can only launch during specific Earth-Moon alignment windows that occur every 2 to 3 weeks. If a crisis occurs immediately after such a window closes, actual rescue time could stretch to 10 to 14 days, far exceeding the maximum survivable timeline for most catastrophic habitat failures. This temporal mismatch is considered an acceptable operational constraint in NASA's